of course, is very good in cost and energy efficiency. And given the antenna gain of phase array and the RHS exactly the same. So after talking about peer-to-peer transmission, we consider if this technology can be used for the to the network. So how to design this sort of multiple access, which we call HDMA, the holographic pattern division multiple access. To me, this kind of multiple access method is a bit similar to CDMA, but anyway, so it's in space domain. So the main motivation is we call holographic pattern division multiple access. We from holographic beamforming to multiple access techniques. Of course, we need new variant of space division multiple access systems, and the user can be allocated in different space domain resources for multiple access. So this gives an example how this HDMA works. So we first map the transmitted data into a single holographic pattern, which relates to signal beams for one user. And based on the superimposed holographic pattern and the RHS will control each element to generate multiple DGR beams. So this slide gives the example of two-user system and 2x2 this RHS surface. So one user, we can see, okay, it corresponds to one holographic pattern, and the other corresponds to its own holographic pattern by the superimposed holographic pattern. This is the weighted and the summation of the radiation amplitude distribution corresponding to each beam pointing to the user. And in this way, the multiple access can be realized. That is a simple example. So in the holographic pattern optimization, actually, it's not that difficult, and it's not needed to optimize the weight of each antenna element. Instead, it's only need to optimize the weighting factor on the whole surface that is good enough. So the complexity is linear according to the it's a linear complexity. So from the in this result, we assume, okay, the amplitude response of this element is a Q-bit contest due to the diagonals, and we try to analyze the performance of the discrete amplitude response. And from the simulations, we see that, okay, in a multi-user, multiple access systems, the 2 bits are sufficient to approximate the sum rate with continuous amplitude value in the multi-user cases, and 1 bit is good enough in the single user cases. So finally, I would like to talk briefly how to design this RHS and how to implement, make it work in the real communication systems. So this is the design target, and we spend a lot of time actually trying to design to make it work. So the target is to implement millimeter wave RHS-enabled multi-user systems as our alternatives to a current energy-consuming 5G base array. The reason we use the 5G base station is we had collaborations with the third largest vendor in China is CITT. They provide us the baseband module, and we use the RF antenna, and we work together to make the system transmission happen. So this is the RHS. Below you can see a number of key parameters, such as the frequency. We use the 6G.5 gigahertz, the bandwidth 800 megahertz, and the polarization is cross polarization, and we use 4 pieces of RHS corresponding to 4 RF chains in order to support 4-stream MU MIMO, and we use the pin dials is like the 1 bit, and the range of the beam is horizontally the minus plus 60 degree, and vertically is minus plus 15 degree. All of these are designed based on 3GPP standardization. So we first need to design the RHS, the small element, and we try to first, okay, select the dielectric material and then design carefully about each element, for example, to set up the diode equivalent circuit and to bridge the gap between the RHS element and the holographic antenna patch. That is the major part. And later on, we can produce, design the 1D RHS array. So based on the 1D RHS array, and then we extend and vertically to the 2D RHS array. So on the left hand, you can see that is the feed. Will send the transmitted signal carried by the reference signal to the surface, and in order to make the transmission and stable, so we use the microstripe power divider in order to divide the reference wave to the whole surface, is transmission stable and equivalently. So we also need to design the control circuit and integration. For the control circuit, the target is to adjust the status of all the diodes. And we use the 1-bit pin diode amplitude control. And when consider, the horizontal and vertical beam direction, and the switching speed is 3 megaseconds, including the control signaling. So the whole simulation, the prototype, is we use, one RHS-enabled transmit sends 2 millimeter wave user terminals, that, as I showed in the very left part, and that is the 4 pieces of RHS, and 1 piece RHS has 384 elements and supporting cross polarization. It has very good performance, and this slide will give a video and show how the whole RHS-enabled communication system works. And can you broadcast it?
Ultramassive MIMO is expected to be a key enabler in 6G networks for accommodating diverse user demands. However, traditional MIMO technologies such as phased array rely on high power consuming and highly cost components, which makes it difficult to scale from MIMO to ultramassive MIMO in practice. Against this background, we have developed the reconfigurable holographic surface for the implementation of ultramassive MIMO. Specifically, RHS's densely packed sub-wavelength metamaterial elements into a compact space, holding significant potential to serve as a highly integrated, low-cost, ultra-thin, large-scale, energy-efficient transceiver solution for future 6G communications. We implement a prototype of RHS operating at 26.2 GHz. The RHS consists of a two-dimensional array of 384 electrically controllable RHS elements. The reference wave generated from each feed propagates to each RHS element and radiates energy to free space. A C-ILC resonator loaded with pin diodes of an RHS element can control the radiation amplitude of the reference wave. When both pin diodes are off, the radiated power is large, but when they are on, it is small. The states of the pin diodes can be controlled based on the control circuit with the power consumption of only 2 watts. To verify the effectiveness of the proposed holographic beam-forming scheme, we evaluate the beam pattern of the implemented RHS. The RHS can achieve the scanning angles from -60 degrees to +60 degrees horizontally. Based on the prototype of the RHS, we develop an RHS-aided downlink communication platform, which are composed of the implemented RHS, user equipments, UE, and a host computer. The RHS consists of multiple subarrays, which is used to transmit signals. The UEs serve as the mobile terminals to receive signals generated from the RHS. The developed RHS-aided communication platform is able to support 2 test cases of multi-user transmission and single-user beam tracking. In the test case of multi-user transmission, we transmit dual-stream signals using 64 QAM modulator. The EVM performance of the 64 QAM signal is 6.93% within 8%. In addition, the achievable rate of the dual-stream transmission in the RHS-aided communication platform can reach 2.1 gigabits per second per user. In the test case of single-user beam tracking, we verify that the RHS-aided platform can provide high-level signal quality for high-mobility scenarios. Specifically, we perform beam training at each position, i.e., the codebook is traversed to select the code word with the highest reference signal received power for communication. It can be observed that the data rate is stable at around 2.2 gigabits per second. Leveraging rapidly programmable metamaterials, our prototype achieves beam switching within 3 microseconds. In addition, we transmit 1080p video using the 64 QAM modulator. The RHS proves to be an effective approach for implementing ultramassive MIMO with low power consumption while fulfilling the transmission rate requirements. In conclusion, this demo is the world's first prototype demonstration of RHS-enabled multi-user communication systems, which has been integrated with CICT Mobile 5G AAAU communication platform for multi-stream transmission. This marks a significant step towards a new paradigm in lightweight, energy-efficient ultramassive MIMO technology. Furthermore, RHSs can be extended to support satellite communications, vehicular communications, holographic ISAC, and other applications.
Right.
Ultramassive MIMO.
Okay. Okay, in the end of the video, I have already give some potential applications, such as to design the satellite communication terminals and for the radar sensing, holographic radar, and also to use like some special areas like the immersive communications. So, but also to support high frequency band backhaul, extremely lost and high data rate transmissions. And already, actually, we did this work very early, like the 90, and published a number of related articles, and from the multi-user MIMO, and also the ASAC and the satellite applications, and recently we did some implementation. And we are going to also deliver a tutorial in Cape Town. So that is the and also this is a column ACK for my collaborators. So without them, and the work cannot be done. So that is. Thanks for your attention.
Thank you so much, Professor Song, for this insightful talk. And maybe we can accommodate one question before the coffee break. Yes, Annie?
Thank you, Professor Song, for the very nice presentation. I just have two questions. One question is because the holographic surface is supposed to have these very densely packed elements, which makes mutual coupling an important element in the analysis of these surfaces, which can actually be harnessed to our benefit. So, you know, in your works, have you considered mutual coupling in any of your works and tried to capitalize on that to maybe realize these super directive beams that these metasurfaces can potentially offer? And my second question is that in the motivation for, you know, these metasurface-based massive MIMO implementations, when we talk about massive MIMO, the main source of power consumption are the RF chains themselves. So even with phased array implementations, we can reduce the number of RF chains to the number of streams or the users we want to accommodate, right? That's the limiting factor. And we can feed that same signal to all those elements in your phased array to get those beam forming gains on top of your spatial multiplexing gains. So with holographic surfaces, I understand that, you know, you can get those beam forming gains in kind of this wave domain using the holographic surface. But can you offload some of that digital beam forming aspect, you know, this number of RF chains, that still cannot be offloaded, right? You still have that constraint in terms of the number of RF chains you would need. So, you know, there have been talks about stacked intelligent metasurfaces in these architectures that can, you know, shift some of that beamforming load to the wave domain and rely on these low resolution data converters to get those power savings from that RF domain as well. So can these holographic surfaces help, you know, in terms of power consumption on that front? Thank you.
Okay, thanks. For your first question, yes, for this RHS, it's, the working mechanism is different from the phase array. It's like serial feeding. Like we just to make use of the coupling effect between each element. But actually, for how to model this coupling effect. We are still working on this. It's not easy, but its phase array is totally different actually. Each element anyway is independent, but there are some coupling effect. But honestly, we are still working on this and trying to model just find out the mathematical expressions, how this coupling effect. So, and when we do the full wave simulations, and we try to actually understand why the spacing between each element is in that value. Actually, for us, it's usually not clear. We just make it actually by simulations. And in your second question, actually, the target of our work is to not going to change the baseband RF chain, actually. So we just want to replace the traditional, this sort of the phase array with RHS. So the digital part, that's the baseband part, and the digital beamforming, and RF chain will be not changed. So if we use the RHS, like we use this kind of the meta surface design method and the piece level manufacturing, we use the diurnode, for example. It is actually very cheap and energy efficient. So that is the way we are working. But by using this serial this feeding method and the beamforming design and the result occasion is totally different from the traditional method because of the leakage power constraint.
So thank you once again, Professor Song. And by this talk, we end the morning session for today. So we'll go now for a coffee break, and I appreciate if you come back at 12 p.m. For the 2 parallel sessions at the other rooms, not the ballroom, where we'll have 2 sessions, one on immersive communications and one on ubiquitous connectivity with a nice lineup of distinguished speakers. So see you again at 12, and enjoy your coffee break.
And then the one that I like the most is really to use this as a platform to do computing. For example, to compute the discrete Fourier transform, and then, for example, try to utilize it for direction of arrival estimation for sensing. Okay, and then I will show you what I believe is, even though there are many prototypes in optics, what is the first prototype that integrates communication and sensing in one platform. This is a paper that is going to be presented at Globocom. Okay, so quickly, I have, I guess, 10 minutes. Now, the concept is this. For those of you who are familiar with RIS, so reflecting surfaces, this technology is different because you don't reflect the signal, but you refract. So the signal propagates through the layers. Okay? So you have a source that illuminates the first layer, and then the signal goes from layer 1 to layer 2 to layer 3 and goes on. So it's a transmissive surface, if you want, okay? But from one layer to another, you don't amplify the signal. You just phase shift the signals. And each layer is essentially one reconfigurable metamaterial. So the connection with the deep neural network is that each layer, each hidden layer is a metamaterial, and each antenna, tunable antenna element on each metamaterial is your neuron. But there is a catch. And this is one of the main complaints, I tell you right now, so we don't complain later, that the strength of metamaterial, of deep neural networks is the non-linearity that you add in each neuron, so the activation functions, which allows you to make them a good approximators. So far, all the papers that you will find on SIEM, they consider linear models. So even though we consider linear models, we get some gains, which is good, but there is still a big jump that needs to be done in order to add non-linearities into the structure and try to tune this non-linearity and to take advantage of that. I tell you this because it's one of the papers that I showed you at the beginning in Science. There was a long discussion that the people were claiming this deep neural network, and then they asked, okay, but where are the non-linearities of deep neural networks? Okay, so that's the reason why I'm emphasizing this. Okay. So now, why SIEM might be useful? I show you three examples. So one is to use it as a holographic MIMO, so you know what it is from Ling Yang song. The idea is A typical base station looks like this, a huge baseband digital processing. So this is the question that Hanni was asked before. So you have high resolution DACs and then a few RF chains and then phase shifters. Okay, that's the typical structure. Now, if you use this SIM, what you could do, in principle, you could completely avoid the baseband processing unit in the digital domain, having a very low resolution DACs. You fire the signal from the antennas and then you do the beamforming, the pre-coding directly in the wave domain when the signal radiates from the antenna, from the antennas. So that's the things, and of course you can build this in the same way as Ling Yang showed you, with this reconfigurable holographic MIMO, where you have the feeders generate the waves, the wave propagates across the surface, and then they radiate, and then they diffract from one layer to another. This is the advanced implementation. What's the gain? The gain is that we know that the analog to digital converters have a power consumption that increases linearly with the bandwidth and exponentially with the number of bits. So if you can reduce the number of bits going from digital to analog, you can also reduce dramatically the power consumption, at least on papers. Okay. So that's the first application, so low complexity base stations to reduce the power consumption and shifting the processing from digital to analog. The second is what I call a multi-layer refracting surface. So for those of you who are familiar with RIS, you know the principle. Usually you put your surface here and you use a reflection. Here you can think of this device, SIM, which is for example put on a window or is put on a wall, and you can do outdoor to indoor communications or room to room communications. Okay? So this is the system model. Now the idea is the following. We know that this was also one of the questions that Annie asked about the mutual coupling, but we know that these metamaterials are usually, especially in wireless communications, modeled in this way. So the elements are assumed to be decoupled, okay? And we model them through a diagonal matrix. That's what we do for simplicity. But information theory tells us that the optimal design is when you have control circuits that connect all the elements together. So you should have a fully connected control circuits that allows you to manipulate in the best possible way the electromagnetic wave. So the model is not a diagonal matrix, but it's a non-diagonal matrix. The complexity of this is huge, and also the power consumption associated with that. So how SIM comes into play? SIM comes into play, okay, in this way. You have one layer, and imagine that this layer has a diagonal response, the conventional one. And then you have another layer with a diagonal response. But then the signal propagates from one layer to another. So you have a cascaded channel, because the end-to-end channel is given by the product of the transmission coefficient here, the transmission coefficient here, and the propagation channel from one layer to another. But now the transmission coefficient are diagonal matrices, but the propagation channel is a non-diagonal matrix, because this is the broadcast nature of wireless communication. So one element here radiates towards all the other elements, and they keep scattering. Okay? So at the end of the day, you have a non-diagonal structure by using this stacked multi-layer implementation. So you can keep each layer simple, and then to enjoy or capitalize on the multi-layer structure to get a non-diagonal structure, which is in principle optimal from the information theoretic point of view. Of course, they are not the same, because one layer, you have one layer of attenuation. You have multiple layers, so you have more attenuation, the signal scatters. But as always, I mean, there is a trade-off between complexity and performance. So I'm not telling you that they are exactly the same. I'm just telling you that you can mimic that behavior at lower complexity, but there is a performance trade-off with this. Okay? So the third example, which is the one that I like the most, and I really am trying to invest a bit on that, is to use this device as a computing platform. You can do whatever you want in principle. I will show you so what's the idea. The idea is that you get some input, the signal propagates through this device, and then you get some output. Okay? So this again goes back to something that people have been working on for a while, which is really performing mathematical operations with metamaterials. Essentially, you can get a wave. When the wave propagates through this material, at the output you can get the first order derivative, the second order derivative. People are also trying to solve equations in the analog domain as the signal propagates through this material. We utilize that as an example for ISAC, for sensing, more precisely, direction of arrival estimation. So imagine that you can get your signal at the input, and then the output, you get the discrete Fourier transform. Now, the matrix that characterizes the input-output relationship of a DFT is this guy here, the matrix F. So in principle, what this device should do and how you should optimize this device. Again, you have a cascaded channel, you have the propagation channel W, and then you have the transmission coefficient upsilon. In this case, I changed notation. You need to optimize upsilon. How do you need to optimize upsilon? You need to optimize all the upsilon in a way that the difference, the distance between G and F is as small as possible. If this is the case, then as the signal propagates through this cascaded channel, at the output you get something that is close to the discrete Fourier transform. So what the discrete Fourier transform allows you to get? I will show you the numerical results. So let me show you this. First of all, what kind of benefits we can get for the base station. So this is the same scenario as Ling-Yang presentation. So we have a multi-user system and we want to serve multiple users. So without going much into the details, first of all, it needs to be understood that the propagation between the layers is near field, so we need to abandon completely the far field model, and we need to have a near field model. This is pretty simple, but at least we take into account the near field model between the layers. Then we write the usual optimization problem, so we maximize the sum rate, subject to some constraints in terms of the power, of course, but also in terms of reflection transmission coefficients that you can apply. So long story short, I'm not spending much time on the algorithm, but in blue you have the state-of-the-art zero forcing beamforming, fully digital, and in red you have the SIM, the implementation SIM. In this specific example, you have a SIM with 7 layers, because we said that after 7 layers the performance were saturating, so there was no gain anymore. And we have 4 RF chains, the same for zero forcing, here for example, and then we have multiple elements, 49 or 100 elements. So the bottom line is that for the same number of RF chains, 4, you can essentially almost double your rate. You capitalize once again on this hybrid structure where you have a few RF chains but many simple elements on the device. It's the same gain as Ling-Yang song showed you when you compared with the state of the art. It's exactly the same principle. Okay? So another thing that you can do with this multi-layer structure, and I think I need to close shortly, but I want to show you the experimental results, so that's just a couple of minutes. So what you can do is really to have a very good beam shaping, which usually is very difficult to get with a single layer. Imagine that you have an area and you want to have a shape like a 2. This could be a street, and you want to focus your signal all in that street and to reduce as much as you want the leakage. Okay, so I skipped some things, but you can see what you can get on the top left with only one layer, L equal to 1. Then you get L equal to 3 here, L equal to 5, 7, and so on and so forth. So you can see that the more the layers, the better your capability of beam focusing, because you have more variables that essentially can be optimized, even though you don't use no linear functions. Okay, so that's not that bad. The last result before the experiments is that if you know the DFT gives you the angular distribution, so how the received power for a given, what is the distribution of the power as a function of the different angle of observations. Okay, so if you get a wave from a given angle of arrival, and then you can compute the DFT, essentially there is only one point here at which you get a lot of power, and all the other points are on the other end very little power. Okay, that's essentially the concept. So long story short, we can show that if you do this processing in the wave domain, you can get performance similar to doing everything in the digital domain, without doing any phase, without requiring any phase measurements in this specific case. And the performance are pretty similar. Okay, so the very last minute, I'm going to show you this platform. So this is a collaboration with this university that they had the platform, and thanks to a connection established by two former PhD students that graduated at Central Sublec, one in my team and one in the team of another colleague. They are now back to China, and so they contacted me because they built a transmit array, a transmitting surface, and then they built a lot of them, 3, and they put them together, they stacked them, and they did some experiments to see whether this structure was working and which was the impact of the multiple layers in this specific device. So I'm not going to give you much information but because of time, but essentially this is a sub-6 implementation, and each element of the metasurface can only apply, is a 1-bit element, so only 0 or 180 phase shift. It's extremely simple, so it's a binary metasurface. Okay, we consider 2 case studies. One is for communications, so we want to go through a wall, we put this surface in front of the wall, and we want to measure the signal at the receiver and to see whether the multi-layer improves the performance. And then we want to do another experiment, which is detecting the direction of arrival of a wave. Okay, so the results are this. On top for received power, at the bottom for sensing. So you can see that as the number of layers increases, if you optimize your device and also the interlayer distance, in this case is lambda over 4 and lambda over 2 for the communication, for sensing it was only lambda over 2, I'm showing you the results, you can see that the received power increases quite well, and also the error in estimating the actual direction of arrival gets reduced. So adding more layers seems to be the beneficial. Okay, so how here the optimization was done is completely brute force. So you will find the two parts in the paper. One part where we develop a nice algorithms, Kramer-Rao bound, etc. So nice for papers. But then you have the implementation part where we essentially did a brute force. So we tested most of the possibilities, and then we got the configuration that was working the best, and these are the results that we got. Okay, so just to tell you, there are a bunch of papers. These are those that I utilized for this presentation. Most of them are done with Chao and his team. They were done by Zhang Cheng Han, who is a postdoc in Chao group. And I mean, if you want to know more, I mean, we are writing an overview with the team. And this is more, the first paper is more an overview that really goes from the beginning, from optical, diffractive neural networks, optics, and metamaterials. And then recently I was asked to put together all the references. This will be published, the second one in EUCAP. It's a state-of-the-art where I put together all the papers published so far, and I try to connect them together. Okay, so there are already 60 papers, more or less, even though it's pretty recent that we started working on that, but there are already around 60 papers only on SIM. Okay. Okay, so that's everything. If you are really, I mean, crazy about these metasurfaces, one of the other degrees of freedom that you can exploit is not to have these flat surfaces that we are all familiar with, but also to have these conformal surfaces. So essentially, you can bend the substrate and try to even optimize how to bend this substrate between the layers. And this could be another optimization variable to control the channel between the layers that now you cannot control. So if you are interested, I'm just giving you a couple of papers. This is one paper under review with Chao and his team, and this is another paper written with NEC in Germany, which was already accepted for publication in TCOM. And here we take into account what Heini was saying, which is basically the mutual coupling between the elements, even taking into account this crazy shape that the metasurfaces can have. So that's all from me, so thank you very much, and if you have questions, I'm happy to take them.
Thank you so much.
Yeah, sure. Thanks.
I've seen some different approaches to the optical computing, and one of the questions that comes up in doing in the analog domain is effectively like a signal-to-noise ratio effectively like a signal-to-noise ratio of the equivalent number of bits. And what is generally the case for the SIMs on this? Are they? I saw a number of 84 dB, which would imply 14-bit accuracy, but that was in the optical band. So you would have to put and do the optical processing at red, green, blue type frequencies. Yeah. Are you seeing that kind of accuracy, or is it less or more? Or?
Yeah. That's a very good question. So we don't have actually a definitive answer at the moment about SIM. So what basically I can say is that by considering the full digital implementation, so essentially we are considering the ideal case where you can control perfectly the signal. So we are not really quantizing the signal and try to see. So we assume that the signal can be completely reconstructed perfectly. With SIM, what we notice is that even though you consider metasurfaces that do not really have many bits, so like you can apply 2 phase shift or 4 phase shifts, I think they are already sufficiently good to get quite good to mimic basically the behavior, the same behavior that you have in the continuous in the continuous case. So this is what I can tell you now. There are not studies, to the best of my knowledge at least, that try to understand the trade-off between the digital precoding and the analog precoding with the SIM. So for example, I could do part of the precoding in the digital domain with a few resolution bits, and then I could do the rest in the analog domain. This kind of studies at the moment, to the best of my knowledge, in SIM was not done.
Just kind of following, does it have to be a unitary matrix, or can it be
that's a very good point. Yes, okay, that's a very good point. So for SIM, is not actually the end-to-end matrix is not unitary, because there is the attenuation between the layers. Okay. Because essentially the attenuation between the layers is a free space channel. It's a typical free space channel like Friis formula, but for near field. So with the RIS, with the reflecting surface, usually is a unitary matrix. The one that I told you is full matrix, but is unitary. So the matrix, okay. But in this case, not. And in fact, there are differences, because when it comes, for example, to study the Kramer-Rao bound and to do the sensing, the limits, the Kramer-Rao bound simplifies significantly when you have this unitary matrix. So the Kramer-Rao bound does not depend on the RIS matrix, but since in this case is not unitary, it actually depends on the matrix. So this has a huge impact. The fact that this matrix is not unitary. Yeah. So this is. But I mean, once again, this is something that we are exploring now in this paper. We are writing in journal paper. We realize that generalizing the analysis for the Kramer-Rao bound, but we don't have a big picture yet, just the first paper that we have. But yes, this has a huge impact. Yeah.
The impact even the quality of the detector side is like added noise.
Yeah.
Not anymore a Gaussian matrix.
Yeah, it's completely different. Yeah, completely different.
Yeah, please.
I agree that the real potential of SIM is for computing as well, and this is something I'm exploring. I'm just worried about one thing when it comes to SIM. It's something you just touched upon right now in your response. It's the attenuation, the interlayer attenuation. I'm just worried if we'll run into the same problem we ran with RIS when we started working on with that multiplicative path.
Yeah.
Because when I did my simulations with SIM, I often see that at some point, when you increase the number of layers any further, you actually see the performance go down.
Yeah.
So it doesn't actually saturate, at least for my case.
Yeah.
And it really depends on how you model those interlayer coefficients. So I'm assuming you're using the Rayleigh-Sommerfeld method for the interlayer. But I think that's a very important point to really look into, because what happened with RIS. I mean, I still believe in RIS. I mean, I worked on it, but how much criticism we had to take, right, with that. So I'm just worried that this interlayer, this product factor that happens is going to become an issue at some point.
Yeah. So it is an issue. So it is an issue. So I can tell you. So in my opinion, there is a problem. There is the same problem that now we have with RIS, that we had with RIS at the very beginning. That the models that people are utilizing for the SIM are extremely simple. So for example, the transmission coefficient has a unit amplitude. There is no back reflection. Everything goes like that. So it's very optimistic. Even though you have this interlayer attenuation, in any case, the estimation is very optimistic because of that. We are trying to work. There is one paper from Bruno Klerks, who utilized the multiport network model that we have been working on for a while, this mutual coupling. So he wrote down this model, but then when he obtained the numerical results, he ignored all the mutual coupling. So now we are working a lot with this multiport network model to try to understand. So I think this multiport network model will allow us to figure out essentially what is the actual link budget. and also what is the impact. But the point is that it's very complicated because, I can tell you, it's very complicated because of the fact that if the transmission coefficient is not 1, the signal can also go back. So, and then what is going to happen in all these interactions between the layers is not clear. So many people say this could be an opportunity to build recurrent neural networks, as long as you can control this, this story. So it's interesting in principle, but if you can control it, I'm not sure.
Gearing up for comments from the reviewers.
This is exactly. So that's the story. Exactly, that's the process.
Thank you.
Okay, thank you very much.
Thank you so much.
So we move to the second talk on the promise of the near space towards ubiquitous connectivity of Professor Halim Yanikumareglu from Carleton University. Thank you so much.
It is such a delight to be here. Thank you for the organizers, Fauzi, Lina, and Marwan. Yes, so we will talk about ubiquitous and sustainable connectivity. And when you hear the term ubiquitous, what immediately comes to mind is satellites from space. But I will not be talking about satellites. There is even a bigger promise, and that is in near space, that is stratosphere, roughly 20 kilometers above the ground. These ideas have not occurred over the last weekend. I have to acknowledge generations of students, collaborators with whom we developed many of the topics or ideas together. Now, in our field, most of the discussions are framed within 6G context, but 6G is rather close. As some of you would know, in about 6 months, 3GPP will have a workshop on release 21, and the key technologies, at least for the first 6G, will be identified. If we are talking about something new and novel, by the way, here we are talking about an infrastructure which is a very slowly evolving initiative. 6G is very close. Therefore, while we try to be grounded, let us put aside the G issues and look forward maybe towards 2050. When we talk about 2050, of course, the discussion becomes to some extent hit and miss. So I just would like to mention that. Humanity has been fascinated about space, obviously. You might have watched one of perhaps the most celebrated science fiction movies from 60s. But when people think about or thought about space, deep space, it is often, or it was often over-predicted. So in 1960s, the prediction was that by year 2000, we will already have a colony on Moon and Mars and so on. That was 25 years ago. Of course, those things didn't happen. And only now, the big promise of outer space, where satellites are, is being realized, and still perhaps that's the tip of the iceberg. But in this talk, I would argue that near space might have even bigger potential. And Professor Slim Aluni is here. With him, we appear in panels and events like that to promote this paradigm. So, every 10 years, a new generation comes and lots of details, technologies, and everything. But if I look at from a bird's eye view, I can perhaps bundle the first 5 generations together. What is the bottom line? The bottom line is it allowed mobility for us. Of course, the device itself, or the mode of connectivity, evolved from voice. Now we are talking about XR, but the bottom line is, again, mobile connectivity. Human person is very tolerant for connectivity interruptions. In a Zoom, if it screen freezes for a split second, you don't realize, or you turn this way, that way, whatever, no big deal. But tomorrow, 2030s, 40s, when there are robots of different types everywhere, then those machines will likely be, at least in some applications, much less tolerant. So we are looking for reliable, ubiquitous connectivity. With 6G, from a particular lens, a new era is starting, and that is towards ubiquitous hyperconnectivity. I want to be connected, whether I am sailing, whether I am trekking, in the plane, and it's not only me, it is the Internet of everything, basically robots of different types, so on and so forth. Eventually, what I want is that my devices would work like my watch. I never think about I am in the plane or here and there, will watch work. It works everywhere. So I don't want to be bothered about how many bars in my device. When I am trekking, I want to wear my XR glasses. When I look at a tree, I should know everything about that and things of that sort. So this is really the paradigm. Now, just before we move forward, Leo mega constellations is something big, and to give you a perspective, there are different types of satellites, at least from altitude viewpoint. Leo goes from a few hundred kilometers to about 2,000 kilometers, and again, as you would know, there are now very many of them. Starlink alone, more than 7,000 satellites as we speak. The old-timers in the crowd, like me perhaps, would say that, hey, wait a minute, this is not a new story. We heard about this a lot in the past. And there were lots of hype, and then big bankruptcies, up and down. Just the same story is happening once again, right? But it is not like that, actually. What this chart is showing is the number of annual launches. And as you see, yes, there were up and downs at these times. What the current time is different is that it is now a hockey stick number of launches. Any graph which has a shape like that, you have to pay attention. It will be really foolish to think that it is same old, same old. It is not. Obviously, there can be turmoil. Starlink may go bankrupt and so on, but those will become details. Something very exciting happening in this domain. By the way, the figure is going to 2023. We are almost 2025. The number is maybe 5,000-6,000 already, and extrapolate to 2030. It's really mind-boggling. So the big paradigm or wish there is direct to device, obviously. Satellites talking to your smartphone. And when we talk about rural and remote, when there is no terrestrial network, certainly this is transformative, this is disruptive, because you have no link, and now I am giving you something. It is really important. But story is different in urban and suburban areas, because there you are competing with terrestrial network. And this is what Van Tonk yesterday, if you were in his speech, he was mentioning that rate-wise, direct to devices 3 orders of magnitude behind the terrestrial networks. Actually, it is probably 4 orders of magnitude. Today, your smartphone can easily get 10 megabits per second pretty much everywhere, downlink, but when we look at the SOS messages, we are really talking about kilobits per second, 4 orders of magnitude. However, mind you, this is the gap is closing. So there are lots of big initiatives, AST Mobile, some of you might know, trying to, here the issue is link budget, basically. The distance is large, and then to some extent, antennas are a little bit inefficient due to the tracking issue. LEOs move very fast. So we have to keep that in mind. And when we talk about the aggregate capacity of a constellation that can deliver to a city, let us say, that is also at least 2 orders of magnitude behind the terrestrial network, but again, getting better and better. In 2 senses, number of satellites are increasing crazy, and secondly, the capacity of each satellite is getting better and better very rapidly. So Starlink, first generation, the capacity was 20 gigabits per second per satellite. Now it is 80 gigabits per second per satellite, and it is again increasing rapidly. Now, we were talking about LEOs at 500 kilometers, which are orbiting. How about we put up a new network in stratosphere, just 20 kilometers above the ground, much closer, and they don't orbit. Like a base station, you attach to some sort of an aircraft. It might be in the form of an advanced helium balloon, or a glider, or a zeppelin, and then basically it is quasi-stationary. This is what is called high-altitude platform station. Cyril was making references in his talk. I hope some of you have heard the term HAPS for the first time today, so that there is something new in these talks for you, but you will hear about HAPS a lot in the coming years. These are some prototypes and artist renditions. The HAPS might be that high-altitude platform station in the form of a glider, but these are big gliders, wingspans 60 meters, for instance, or a zeppelin 135 meters by 65 meters, a huge bird in space, or these are some NASA concepts, advanced balloons, another project funded by Deutsche Telekom. This is an uncrewed airplane with hydrogen fuel. But let me park those to the side and just differentiate high-altitude platform stations from, in particular, LEOs. First of all, this is very close to the Earth line of sight, 20 kilometers. As a matter of fact, LTE standard supports 20-kilometer connections. And something which is not very apparent to some people is one might think that, hey, 20 kilometers way up. It is not necessarily like that from a path loss viewpoint. Interestingly, you might have a small base station just 141 meters away. If the path loss is 4 in a cluttered environment, that is the same path loss with free space path loss exponent, that is 2 at 20 kilometers. It is a little bit, counterintuitive, but it is like that. Due to how the power attenuates, if you have a free space path loss situation, path loss may not be that high. And the fact that this is not orbiting is a big advantage. You don't need to track things. It is much easier to create big antenna patterns and have better directionality and gain, but more importantly, very scalable. When we design satellite networks, it's always worst case design. You put as many satellites as possible, or sufficient number, so that in the region where you need, there is a sufficient number. Most of your satellites will be over the seas and places where you really don't need them to be, but since they are orbiting, they have to be there. HAPS is not like that. You need in Abu Dhabi, you just put one on top of Abu Dhabi, another in Dubai, and then it can scale up like that. And since it is huge, it can carry a lot of equipment. Today, the lift capability is in the order of a few 10 kilograms in many of these projects, but it can increase to a few hundred kilograms. Remember, I don't have 2030 in mind. I'm just trying to look forward, and this can progressively increase to a ton of equipment. Imagine much more equipment than your macro base station. And then why are we only talking about connectivity? How about cameras? How about sensing for localization, positioning, navigations? Really, the sky is the limit, if I may say. And basically, in particular, the urban and suburban regions can be a very important use case. Just on the intelligence, surveillance, and reconnaissance kind of example, this is a recent image from SpaceX's launch facilities, from pretty much the best you can get with commercial satellites. At 620 kilometers, the resolution is 30 centimeter per pixel. Now, it is public knowledge is limited, but it is known that spy satellites actually at lower altitudes can have much better resolution in the order of 5 centimeters per pixel. So what does that mean is that in this photograph, actually, if you enlarge, if there is an object by 30 centimeter by 30 centimeter on the ground, you can detect the presence or absence of that object. You may not be able to recognize, but you understand that there is something there. Now, this is 2024. How about 2030s, 2040s? I'm not talking about few hundred kilometers, but 20 kilometers, ultra cameras with AI-aided techniques. So it is possible to improve progressively the resolution to millimeter per pixel. And actually, the low resolution images for face recognition, so on and so forth, starts about 1/3 of a millimeter per pixel. So we are almost there to recognize human faces and distinguish who is who from HAPS. So this big brother, big sister watching you 24/7, good news or bad news, I just leave it to you. So a diagram from one of our magazine papers, lots of beams for different reasons, use cases. If it is IoT, very big beams. If it is capacity, it is pencil beam widths, beams for air traffic and other reasons. But as I said, connectivity is just the start. I generally give this example. At some point, all the vehicles might have rooftop antennas, and you can detect any traffic infringement from stratosphere. Now, I just have about 5 minutes, I guess, right? So, what's that? Yeah. So, I would like to change the discussion to sustainability viewpoint. Imagine that DOT is a tool bus, an autonomous bus moving in the outskirts of an urban area. So from the very basics, we know that in order to have good spectral efficiency, especially let us say FR3 band and so on, it needs line of sight. You deploy infrastructure so that a user is pretty much always statistically close to an access point. And that is a very bad design. You put infrastructure to get capacity. If there are many users, that is good, there is revenue. But if you start putting infrastructure for coverage, it is bad news. It is high capex, it is high opex. Most of those cells will be empty most of the time. And then we really don't want to have a situation like that so that we can wear XR goggles, right? It is not only ugly, but it is not green, not sustainable really. So, what might be a better way? Well, at least for outdoors, why don't we have, like satellite communications, spot beams from near space? So whenever I need capacity, all the capacity is centralized, nothing is wasted. If I want to give connectivity to a group of users there, I just turn on the spot beam, and once that need is not there anymore, I turn off that spot beam, that capacity is moved elsewhere. This is a much better architecture than the worst case design which we are accustomed. So these are my beams on the ground for, again, variety applications, different beams. My tool bus is at the corner, so a dynamic, perhaps phase array or a spot beam is just tracking that tool bus, so I don't need to over-engineer, I don't need to over-densify. I will talk more details next week in MECOM, Middle East Conference, on more technical details. It's more a high-level talk, but I would like to make a very rough calculation from sustainability viewpoint like John did in his talk yesterday. Imagine we have an 100 kilometer by 100 kilometer urban suburban area. There is terrestrial network, not over-densified, so for basically predictable traffic. But then there are users in that 10,000 kilometers square. They are stressful to base stations or the network. Why? Because their spectral efficiencies are not good. In order to save those links, either you have to kick in more power or more bandwidth. So basically, we have about 10 to the 10 meters square divided by 1 million persons, one person on average every 10,000 meters square. Now, if I can create hotspots, really virtual cells around those people with, let us say, 100 meters square area per person, there is a 2 order of magnitude gain in energy. I'm not talking about percent, 2 orders of magnitude. Because in the first case, when you do this illumination by terrestrial network, you are giving coverage everywhere. There are no users. We can do better than that with from stratosphere. So even if I actually this can be even better if I can make narrower beams 10 meters square area per person, then the gain is 3 orders of magnitude. If this is a very rough calculation, maybe it is 1 order of magnitude, but as they say in statistics, rough order of magnitudes 1 to 3 in network energy savings. Anyhow, I have to wrap up my talk, but every generation we are talking about maybe 2 orders of magnitude increase, give or take a little bit, by several generations. So in 6G hotspot 1 terabits per second, maybe a little bit generous, is under discussion, and I assume it will be just a matter of time that we will be talking about 100 terabits per second in 2040s. Well, today, as we speak, Viasat-3 satellite, it is a high throughput satellite at geo-orbit, can deliver 1 terabits per second. Now, if you are thinking that, hey, this is an awfully high number, there is no magic. There are 1,000 spot beams, like 1,000 sectors, if I use an older terminology. 1 gigabits per second times 1,000, it makes 1 terabits per second. So if in 2024, we can achieve 1 terabits per second from 35,000 plus altitude, I have reasons to think that time will come in not too distant future, we can give 100 terabits per second from 20 kilometers. Basically, our 50 years of know-how and expertise from terrestrial as well as satellite, they can be brought into near space, because near space from one angle is like terrestrial network, and from another angle it is like space network. Anyhow, I think I will just move forward at the interest of time. Basically, a key idea in these HAPS constellations is that I have shared resources. From sustainability viewpoint, we know from the very first principles of traffic engineering, it is best to pool your resources, whether it is antennas, electronics, storage, you name it. And then with bird's eye view of a large area line of sight, it creates lots of opportunities, whether it is connected vehicles, autonomous, I meant connected and autonomous vehicles, UAVs, so on and so forth. So if I would like to make the digital twin for vehicles, for traffic of Abu Dhabi, why I should rely on 1,000 small cells and stitch the data together? I can do that from stratosphere, because the HAPS sees the entire greater Abu Dhabi region. Anyhow, so there are many research areas, pretty much anything and everything one is working on, from physical layer to edge computing to AI for orchestration management. You can do this in this much bigger three-dimensional network. Anyhow, with my team and other collaborators, we have looked at this angle as a concept. Lots of magazine papers, lots of technical papers. I'm not getting into the technical side more recently. Antenna design is very important in these advanced systems because you get most of the gains and interference mitigation through advanced antenna structures. If you are interested, these publications are available at my website. In conclusion, non-terrestrial networks is not a single technology, but it is a big infrastructure project. And HAPS is a layer of them in stratosphere. This is not an alternative to terrestrial or space networks, but for better working, sustainable, ubiquitous operation, it can be an important layer. And if you are thinking, hey, is this possible? Why not? As we speak, we have the space network, 7,000 satellites alone in Starlink. We can certainly have this in stratosphere as well. Now, if you found this paradigm interesting, I'll be more than happy to collaborate, work together, or have discussions with you towards a new architecture towards 2050 for wireless connectivity. Thank you.
So much.
Okay, let's see if you have.
Just a quick one. You are putting all your eggs in one basket, right? So you are getting off of like all the terrestrial network.
I am not. This is always repeat. This is just this is not an alternative to the terrestrial network. For instance, if you are just outside having your coffee at the patio of a coffee shop, and just across the street, 50 meters away, there's a small base station. Why do you deal with near space or space? Connect always there. But there will be situations, actually most of the cases, it won't be like that. So my premise is that rather than stressing the terrestrial network and as a solution over-engineering it, putting a base station at every lamppost, I have a better way of doing that. Have your terrestrial network for kind of median and predictable traffic. If there's a bus stop, there will be users there. Of course, it makes a sense to put a small base station. But imagine again an 100 by 100 kilometer greater Boston area, for instance, right? So there are lots of suburbs and so on and so forth. Their help from stratosphere is very important. But coming back to the city, our discussion goes beyond connectivity. That guy or woman who is having her coffee, I can see her and know that that person is having coffee there with my cameras, sensing and so on from stratosphere.
A quick question. Thank you, Harim.
Yes.
So terrestrial versus non-terrestrial. So what are the bottlenecks when it comes to the channel models? Because let's say, like the promise of non-terrestrial is there when the channel is clear, when there is no obstacles, no clouds, no.
Sure. So of course.
What are the channel models that you need?
Yes, a fair question. Here we should really not, in any religious way, bet on one technology or one layer. So it is about good engineering. We have several options at any instant. Whichever option is best, I guess we will just go with that. Going back to the coffee shop example, again, your connectivity is with the small base station, but then there is a truck, just stop at the traffic light, you lost line of sight, and then the signal might go to the HAPS, for instance. So indeed, for radio communications, weather conditions is no big deal, but basically, if you don't have line of sight outside, you know, the experiment is quick. Just look above if you see the skies or not. In some city centers, you may not, due to high rises, so on and so forth. So then we will be relying on reflections and so on. There are no good channel modeling techniques for HAPS in urban areas. There are lots of studies in suburban areas. The reason is that this concept has been articulated in the old days for rural and remote. But remote, especially now, satellite is a very good solution for that, at least for some use cases. Here our interest is more in urban areas, and in dense urban area there is no good models at the moment, so there is a lot of research to be done in a variety of ways. Actually, maybe as a conclusion, I will just mention two big challenges which are as a matter of fact, outside ICT. One of them is having a long endurance good aircraft. That is an aerospace, aeronautics discussion, but it is a challenge. And secondly, where will all energy come from? The photovoltaic cells and the sun energy, it is good for a 5G base station, but if you want to add more functionality, edge computing, data center, cameras, everything, that will not cut it today. So it is a big research topic as well. Therefore, many projects rely on uncrewed aircrafts, airplanes with hydrogen fuel. So it is really a paradigm unfolding in front of eyes. There is room to do research from very many angles indeed.
I would like just to remind the audience that nowadays we are thinking that everything is in the ground, but the future we will have taxis flying. Actually, Dubai is one of the leaders next year or the year after. We will have the first test of flying highway on the sky. And one of the things that the people ask us is to monitor and track this flying, let's say taxi flying or drones, okay, even for merchandising. And the problem is nowadays the network on the ground is there is no connectivity in all the places, and actually because we are waiting that the operators change the antennas of the 2D antennas to 3D antennas. That means so this could be a complementary. This could be a complementary because this is very geolocation. Any country for specific, you will have highways of this flying taxi, flying drones for merchandising on specific areas for security also. There is people also actually in Dubai looking what is the best path over the high sky point of view of coverage and security. So we're working also on that. So one of the options, I will not say this is wonderful and will solve everything, we can deploy very specific geolocalizing hubs, different altitudes, different technology, to just the monitoring and tracking the doors, because it's forbidden to lose any one of these flying.
It could be any different than planes, right?
Yeah, okay, planes.
Lower altitude.
Yeah, it could be even less than 500 kilometers. It could be. We can discuss after on the lunch. Okay, there is also security issues. There is these national security issues. Okay, there is a lot of things behind. So thank you so much, Halim. We passionate the audience with so much questions.
Okay,
we will move. Use the microphone or just.
Do I need to use a microphone? Do I need to use a microphone? Maybe not? No. Okay, so
Ali.
Well, yeah, thank you. Well, thank you for coming and for giving me the opportunity to present today. So, Li-Fi, light fidelity, transceiver design for 6G. So there's a lot of things to defend here. So Li-Fi for 6G, well, it was promised to be for 5G. There is no promise that's going to be done for 6G. So let's say for XG, okay? Now there's a few messages, take-home messages that I would like to convey. Now, but before doing this, it should be
escape. Yes.
Okay. So this work was done by my former PhD student, Amin, and he's now with InterDigital, and my colleague, Shadi Asi at Concordia University. And also, I would like to acknowledge Herald Hess Group
So my students spent several months in his lab doing experiments. So the work that I'm going to present today was based on, Marco knows, based on the experimental work that Amin did at Herald's in Herald's lab. So like this is the outline. I'm going to go through this quick, so I will not be emphasizing equally on these topics. The background, the system architecture, the channel models, and the multiple access techniques that that we used, and also we will be incorporating what we call the spatial modulation or space shift keying. That's something that we've done like a few years back, and now it's a part of the standard as an option in 5G. Okay, so what do we want to achieve in 6G or 7G or in general? So we want to have massive connectivity, reliability, security, low latency, all of these things happening at the same time. Well, obviously there is a lot of constraints and contradictions or clashing interest in this. So the kind of things that we look at is what kind of resources do we have in terms of hardware resources, software resources, and then we try to work our way through what we have available to us with the least complexity and cost. So with all of these constraints, radio frequency has been efficient and has been effective, but then in certain situations it might not be the solution to every single problem that we have. Okay, so in particular when it comes to indoor communications. So in indoor communications, we resort to Wi-Fi or to using light as a means of communication, and the reason for that is that because we already have light fixtures everywhere, so why not use them for communication? Okay. Well, obviously it doesn't mean that Wi-Fi will be a replacement for RF or for Wi-Fi. It will be just complementary in places where RF is inefficient, or maybe maybe for safety or maybe for security, for different reasons. Yes, so this is something that you already know. So we have obviously with light, because we have an abundant amount of spectrum that is not even regulated, that we can utilize, for improving the communications that we have. Okay, so we have the infrared, millimeter wave, infrared, visible light, and then the ultraviolet. So for the uplink, they use the infrared, and then for the visible light communication, Wi-Fi, downlink, they use the visible spectrum, for convenience reasons. Okay. So for the high frequency, so the millimeter wave, the terahertz communication, and then we have the optical wireless communication, and this is what Slim was talking about, today. Okay, so and this becomes very, the free optical, FSO becomes very efficient when there is line of sight, and when the receiver is connected to the backhaul, it becomes efficient. But then for visible light communication, it's a bit different because there is mobility, there is phones, so the system is different. And this is what we will be focusing on, not FSO, but more on visible light communication. I think John Chiaffi, he mentioned in the first in the keynote yesterday, were light, because we are lucky because we have light, and then light was used centuries ago as a means of communication, but in a different context, obviously. So these are like I said, the spectrum or the frequencies that we'll be utilizing for the OWC. Now, one thing also when it comes to radio frequency, when you're talking about 5G and 6G with the millimeter wave, and then there was a lot of hype about millimeter wave, but then with experiments it was proven that millimeter wave cannot work everywhere, especially when there are obstacles. Okay, so and then also it's short range, so that's why this has to be complemented by something else. So this is kind of gives a comparison between the different frequency bands and what can they achieve and what kind of obstacles they have. Okay, so for the VLSI, visible light communication advantages, yes, obviously large bandwidth, and it's unregulated. High speed, high data rates. Now, one might argue that, well, you cannot build an end-to-end system based on VLC, so it has to be connected or like to have to be working with an RF system. So then the RF system becomes like the bottleneck. So you have a VLC, but then you have also at the outside you have the RF, and this could be an obstacle, obviously. Okay. Yes, unregulated green communication safe because sometimes you're in a hospital and then you're supposed to switch your phone off, or you'll be like on the airplane and then you have to switch your phone off. So radio frequency can be hazardous, but then with VLC, this solves at least part of the problem. And then low cost because we already have the fixtures, like we just have to fix, to amend them, by like low cost, devices to do that. Okay, so like also when it comes to safety is another issue, and then what's not mentioned here is the is security. So RF waves, like they go through the walls, whereas Clyde does not. So in this case, if you want to secure your communication, it will be achieved through that. VLC applications, and then one of the applications that I think Herald was demonstrating this, where, so let's say you're on an airplane and then you're seeing a video on your screen, and then, well, if you are told how that signal arrives to your screen in front of you, there's a lot of like bundles of wires under the seats and all that stuff. So this could create like a problem, like hazardous like safety problem. One possibility would be to have the video projected from the light, like just above your head on the screen. Now, yeah, that seems to be a feasible solution, but then one problem is, what if you just block it? So because you would require a line of sight for this to work. So I mean, it doesn't really fix all the problems, but at least it will complement or solve some of the problems that we have. Okay, so it has been progressing. So yes, VLC was supposed, or like let's say Li-Fi was supposed to take off years ago, but then there are some challenges facing VLC, or a lot of people they don't believe much in it, and especially some companies. But then there are some, I'm aware that there are some contracts or some companies, especially in specific applications, like military applications, where they do use that. Okay. Okay, so the system architecture, so this is like a typical thing. So we have the some signal processing, and then D2AC, and then we have the downlink, and then you do the reverse. And so we said that for the downlink we use the visible light communication. For the uplink, which is like the infrared, like I said, because of the for convenience purposes. Okay, these are some of the devices, transmitter receivers. Okay. Like one of the challenges is that it's not really a main challenge, where the signal, like the modulator has to be like a positive signal, but then it's easy to do by having a shift, like a DC shift. Now when it comes to the system model, so here what we have, Y is the received signal and X is the transmitted signal, and H is the channel gain, and we have the noise. There are two types of noise. We have optical noise and we have the electric noise, but then they are all combined as a Gaussian model, as a Gaussian noise. Now H is the channel coefficient. Like we already, this has been well modeled in RF communications and RF systems, but when it comes to VLC, what is H? So in many scenarios or many papers, probably they assume that very idealistic H. I think Murad did some modeling, channel modeling. So in this talk, we'll be talking about some experimental work that was used by Herald's group and my student to come up with a model for an indoor communication based on experimental results. Now, the significance of this is that because we need to have an accurate H, an accurate channel model, to be able to design whatever signaling scheme or whatever detection scheme that without H, it's useless. Whatever you do, becomes irrelevant. Okay. Now, H is I think I'm going to mention this. So I think before that. Okay. Now, the most of the time, like before before we used like spatial modulation or space shift keying for Li-Fi, like on-off keying is the common practice. So, but then this could be problematic because of the flickering, effect when it comes to this. But this is like one of the challenges, and plus the signal has to be positive and all that. But again, these are not major obstacles. Okay, so now we'll be focusing on the channel model, which is H. So we know that because the frequency is very high, so the wavelength is very small. So multipath fading is not an issue, and small scale fading is not an issue because the size of the receiver is much bigger compared to the wavelength of the signal. Okay, however. Large scale fading becomes an issue, which is like the path loss. Okay, the path loss becomes an issue. Okay, what else? Yes, it doesn't experience like the multipath fading, and also the Doppler shift is not an issue as well. Okay, so we have Doppler shift similar, unlike RF, Doppler shift is not an issue, and also the multipath fading is not an issue. Okay, so large scale fading is an issue, which is like the path loss. Okay. So now, unlike, let's say, FSO, when we talk about Li-Fi, what kind of things that are significant that we need to take care of? Well, like most of the time we are communicating with a hotspot. It's like a Li-Fi hotspot using laptops and using phones, right? So, like, what are the scenarios? The scenarios would be stationary. So we are sitting down, and then we are connected to the Li-Fi hotspot, or we have a mobile. Now, the challenge is, like, let's say if it's a laptop, and then if it's equipped with the transmitter and the receiver, it should not be a problem, right? Because it's stationary, it's fixed, no issues. However, when you have a phone with you, now the phone it can be in many different angles and the rotation and the orientation and all that stuff. So this is what we are focusing on, basically, to model the channel between the mobile and the Li-Fi hotspot, like using a statistical model based on the experimental results that was done. Okay. So what has been done was like idealistic, apart from what Murad has come up with similar channel models for the channel gain. Okay, so the device orientation, like, it does affect. So for instance, like, where the transmitter, the receiver is, or the photodiode mounted on your phone, it does make a difference. Let's say if the hotspot is in this direction, and then your phone is like this, and then the receiver is on this side, there's a blockage, right? Because like we need that connection between the two. Mobility. So let's say if you are talking about phone, not like, let's say, a laptop, then mobility becomes an issue as well. And also, you can have access points similar to a cellular network, where there will be multiple cells. You are crossing from one cell to another. Blockage is another thing, okay, because that line of sight is essential in this case. Okay, so then there is like some modeling. We model like alpha, beta, and gamma, which is like the rotation, the three-dimensional rotation of the device, by using those models. And then without mobility, so there were some channel models that they were developed again based on experimental results. So they were modeled for different values, but again without any mobility. Okay. The device orientation, now also you can represent it using those angles, because you want to have an expression at the end that is a function of all the parameters that we can come up with. The elevation, the azimuth, the direction. So this is the probability density function of the channel gain when for a sitting while the person is sitting, and then when we have the walking. So like we have different scenarios. Okay, so what else? Yeah, so like it's because what has been used so far before, like more the uniform distribution, but then it's not really very accurate if you compare them. Okay, with the mobility, now incorporating the mobility into this. Okay, so just to give you the final thing, because I didn't have much time. Okay, so these are the expressions that incorporate the orientation, the mobility, and in scenario on the left-hand side we have the sitting activities, and on the right-hand side we have the walking activities, that for different parameters. Okay, so this is a comparison. So like on the left-hand side, like we have the simulations, like in the green one, and then the exact PDF based on the numerical values. Okay, and you can see like how close like the experimental results versus the analytical results. The same thing on the right-hand side, like we have the CDF. This is for the walking. As you can see, there is an excellent match between the two. When it comes to the performance, like I said, so when you have whatever scheme that you come up with, like you really need to use the channel model, the actual channel model, and this is what we have for the actual channel model, like based on the experimental results. This is for the sitting, and then also we have for the walking activities. So as you can see, like there is saturation in this case. Okay, as you can see, like as the transmitted power increases, like the bit error rate, saturates. Okay, so now we need to look at different signaling methods. Okay, so which brings us to what we call the transceiver design. So in this case, the typical signaling scheme is the on-off keying, but in on-off keying it has some limitation. So this is the approach one. And then we will go to the second approach, what we call the multi-directional transceiver. So consider, let's say this is a mobile, and then you have, let's say, 4 receivers. So one option is to have those 4 receivers, let's say, mounted at the bottom and on one side of the phone. Well, you have diversity in this case. But then what happens is, if you are in this position and the Li-Fi hotspot is on that side, well, obviously you are blocked. Okay, so like this is one scenario. Another scenario would be to mount those 4 receivers on the edges, like on different sides. So in this case, if you change the orientation, well, still you have more connectivity with the hotspot. So we're not increasing the complexity. It's just like more of the placement of those antennas. So like this is an experiment where we have, think of it as a ceiling with multiple access points, and then here we have the squares, we have the receivers, L1, L2, and then L3. As you can see, the multi-directional receiver, the performance. Okay, so as you can see, like the performance goes like this, so the error flooring, disappears because of that. When we have the screen, what we have on one side, so the antennas are not displaced on different sides of the mobile. When they are on one side, stuck to one side, so you can see like this performance. But and then the other one is more of the on-off keying. So on this side, what we have line of sight, and then we have non-line of sight. As you can see, like let's say this one, the MDR. So line of sight plus non-line of sight. And then we have when we combine the line of sight and the non-line of sight, obviously the performance will improve a lot. Okay. All right, so what else? This is for the walking, this is the CDF. There's a huge improvement. We're using spatial modulation. Probably some of you don't know what spatial modulation is. Let's take a simpler version of spatial modulation, which is space shift keying. So space shift keying, like let's say when we go from BPSK to QPSK, we double the bandwidth efficiency, okay? Because we increase the modulation size. With space shift keying, if we don't want to increase the dimensionality of the signal, we can use the antennas, the antenna indices, to convey information. So for instance, let's say if you are talking about 4 antennas, you start with 2 antennas. It's like binary, BPSK. But then the information, the signal itself does not carry information. What carries information is the antenna index, which antenna was activated. So when you have 2 antennas, then the bandwidth efficiency is 1.
When you have 4 antennas, then whichever, let's say if one antenna is active, that means you're transmitting 2 bits per second, so the bandwidth efficiency doubles. If you're talking about 8 antennas, then it triples. So you might say, well, is there a problem with this? I mean, nowadays, because we are talking about millimeter wave communication and high frequencies, so mounting hundreds of antennas on the base station is not an issue. So that's why, yes, before, maybe like in 3G, that the concept of spatial modulation or space shift keying was an issue, was a challenge. But now with high frequencies, it should not be an issue. So now in this case, we're using spatial modulation. So not only are we increasing the constellation size, we are also using another dimension, another degree of freedom, which is the number of antennas in this case. Okay, so this has been the case. And now this is, so let's say the handover. So think of this one, transmitter 1, transmitter 2, and each one of them has a certain coverage area. And then, so this is similar. It's not any different than cellular communication. Okay, what is? I'm going to skip. How much time you have?
We have 4 minutes more.
4 minutes, okay. Now, multi-user VLC system. So what's left here, what I want to really convey is that whatever is done in cellular or RF communication can be done using Li-Fi communication or VLC communication, which means multi-user communication is there. Let's say the handover. So because think of it as each transmitter or each access point, think of it as a base station that has a certain coverage. Right? And then you can have some overlapping, and then the users are in the overlapping area can be served by 2 base stations, or if you want, you can decide, to hand over that user to be served from this space station to the next space station. So that it isn't any different. Once you have the channel model, everything is possible. Whatever is done in RF can be done in VLC. The same thing for the multiple access. You can have frequency domain, time domain, and then you can have the CDMA concept. Both of them, you can have NOMA as well. I'm going to skip some. Spatial diversity, we have a multi-user communication system, so we have multiple access points, and then we have multiple users. Whatever is done for RF can be done for VLC without any problem. Okay, so in this case, you can also explore the spatial diversity, the user diversity, cooperative user communication. Everything that was done for RF can be done for this one. The pre-coding. Because to me it was similar to because when I was doing my PhD, all my work was on signal processing and channel coding for magnetic recording. I've never done wireless in my PhD, but then channel coding, you already know what it is, and signal processing, equalization and these kind of things. But then when I moved to wireless, you can do the exact same thing. It's just the channel changes, well, obviously with its own challenges. Spatial modulation. Okay, so I already explained what spatial modulation is all about. So the lid selection, yes. So in that case, let's say if you are talking about a user that can be served by multiple access points, but in this case you can select the access point that has the strongest connection between the user and the access point. The spatial diversity that we talked about. Physical layer security, we've done a lot of work on the physical layer security, and then the secrecy rate, and then you can do beamforming and all that, similar to what's done in RF. Okay, what else? Yeah, so we examined also, we studied the secrecy rate achieved by, in this scenario when you have a source and we have an eavesdropper and a legitimate user, you can do beamforming, you can do artificial noise, to increase the secrecy rate. And also what matters in this case, let's see if the separation is large enough between the eavesdropper and the legitimate user. Well, in this case, the secrecy rate does not deteriorate by much. So we considered in this case number of access points, and then we have legitimate users in green and eavesdroppers in red. Then whatever we did for RF, it was done also for for this one. What else? I'm not gonna skip this. For indoor localization, this is something of interest, obviously, and we can do the same thing with VLC. We can invoke, these are like the present technologies, but then also we can use VLC. In this case, also you can deploy or you can employ deep learning, for indoor localization. And also, not only that, you can also track a mobile target. And the way to do this, you can use deep learning methods. So you can, when an object is moving, you can also predict what the projectile or the path that object is going to take, and then you can predict it based on. So this is for the stationary, and then you can do it for the. Obviously in this case you map the entire area into smaller squares, and then because it's already mapped, like you already know what the space is, and then you can predict where the object is moving. In this case, we're invoking deep learning methods. Is this done?
Yes.
Okay. Anyways, so I'm gonna end it with. So where is this going? I mean, still there's a lot of work that needs to be done, especially when it comes to channel state information as well. But this is for the indoor. What I've done was for the indoor. For the outdoor, it's a different ball game, because in this case the distortions and then the noise it's very different. Okay. However, it's being considered. Channel models are needed as well, and the integration between RF and VLC also is another challenge. Okay. So hopefully, if we don't see it in 6G, it will be in the next generations. Thank you.
Thank you, Andy.
Any questions?
I think we don't have really time. Okay. Sorry.
Okay. So
we can you can discuss later on.
Okay.
So we move to the next presentation. I mean, always the last presenter is a bit painful because he has to leave all the very function.
Yeah, can I use my new slides? Yeah, can I use my new slides? I just this one. Copied this one. Yeah, so it's better. Yeah. I just want to save time for everyone, so because I do not want to delay your lunch. Yeah, so I just shorten my slides and yeah.
Big difference with what you have?
Yes. Yeah, so it's
great.
This one, right? Okay.
Can you come from that side?
Okay.
With this?
Yeah, this one. This only one. Yeah. Okay, great. Yeah. Okay, great. Yeah. So very excited to be Abu Dhabi again. So I have been here for several times. This is perhaps my 5th time. Yeah, so every time when I landed, I feel very excited because here it's very spacious, right? So I came from London previously and very crowded and tight. Now I moved to another more like tighter and more crowded place to the University of Hong Kong. Yeah, so but I'm still keeping being professor in London. Yeah. So today this is my topic. So yeah. So first let me control the time. Yeah, we'll see. I will try to finish this in 20 minutes, okay? And in that case, I will not delay your lunch. Yeah. So I will first give a overview of what is near field effect, and then what is sensing basics, and then from the far field sensing to the near field sensing, and then point out some research opportunities. Yeah. So let's start with the first one. So what is near field communications? So what do we mean near field, right? So actually there are 3 technical trends for the building up 6G. So we have larger and larger antennas, right? So previously we have MIMO, then massive MIMO, then extremely large massive MIMO, then perhaps holographic MIMO, this kind of thing, right? So then we go to the higher frequencies. Previously we do the sub-6 G, then millimeter wave, then terahertz, right? And we have the new forms of antennas. Now we have different forms of antennas, like the rays, like the star, like holographic MIMO, like the SIM, and also for the continuous antenna, we have different, for movable, fluent, flexible antenna, a lot of kind of different antennas, right? So when we make the near field communication, what's the physical difference, right? So let's talk about this kind of near field. If you search near field communication, NFC is not a new word, right? So it's see that people in the 20 years ago started to work on this kind of area, near field communication. But for that kind of near field, they are reactive near field, right? So it's more like, so we use this contactless. We use your credit card, where you use a room key, right? So this is called reactive near field. And for wireless communication people, right? So for a long time we focus on this area, radiating far field, right? And how about this time, this radiating near field, right? So actually for a long time people ignore that. Right. So I share some stories why I want to focus this area. Previously, when I was working on STAR, and one of my students, he talked with me. His background is more like physics. And I said that, okay, let's form a model with blah, blah, like this. And he asked me one question. So why do we want to use this kind of planar wave to do this kind of modeling? All the electromagnetic waves, they are like spherical waves. Why do you want to use this planar waves? So I was a bit shocked. So I never thought about this problem at that time, right? So then I have a deeper look at this one. I said, okay, so this is the only difference, right? So now the only difference from between the near field and far field communication from the physics perspective is that, so in near field we use a spherical wave, and the far field we use a planar wave, right? So. But you may argue that why people do not realize this problem for last 20 or 30 years, why people still use this kind of planar wave. I show you something, right? So if you give me an example, so for example 50 gigahertz, right, and perhaps 10 antennas. So the near field region is just perhaps 0.24 meter. In that case, it's very short. We can just ignore that. We do not really care, right? But now things are different. Because we have higher and higher frequency, we have larger and larger antennas. We have the new forms of antennas like star, like rays, so we can put this just on the door, on the ceilings. We can make it very large, right? So this is very different. So currently, for example, for 60 gigahertz, and this antenna is 0.5 meter. Yeah, 0.5 meter. It's not like that, just like this. The near field region can up to 100 meters. In that case, we cannot ignore that anymore, right? Even if it's just 20 meters, 10 meters, it's still very useful, right? Even if we are talking about this room, how many meters is it? Just maybe up to 10 meters, right? So this is why we need to investigate near field communications. Yeah. So now let's see what will be different. Mathematically speaking, previously I talked about physics, physically speaking. Mathematically speaking, the only difference between the far field communication and near field communication is these two equations. For far field, actually this is a planar wave, right? So if we calculate this, actually we use d cosine theta to calculate it. Right? And if we are talking about near field, right? So we use this, we do need to rely on the cosine theorem to calculate this RN. Right? So this is the only difference for mathematical speaking, right? That's it, right? So what, right? So let's see how can I move this a bit further, right? So we play with some mathematics. We do this kind of Taylor series, right? So for example, this is Taylor series. Do this 1, 2, 3. This we keep the 3 atoms, right? For the far field communications, actually we just keep these 2 atoms. For the near field communications, actually we keep this 1, 2, 3, these 3 atoms. That's it. Which means that, theoretically speaking, far field is the special case of the near field communication. And the near field communication is the more accurate representation of the far field communication. This is the difference. Right? So you may argue that so this is just so boring, right? So I just want to know what's the benefits of near field communication, right? So we talk about a lot, right? So what's the benefits? Let's move on this a bit. So previously, if I ask you a question, So we do not have, we just consider line of sight. We do not have scattering. So what is the DOF, or what is this kind of DOF of the memo communication? No scattering. It's just one, right? It's just one. It's just the DOF is one. It's one matrix is one. Right? If you consider the like loss and the far field, no scattering, right? But so it's not really the true case, right? So if you're near field communication, actually we have multi-paths for this kind of line of sight, right? Which means that so we can have the high rank matrix. We use this low rank matrix to multiply this high rank matrix. We can have the larger DOF. Right? So previously, many people will ignore this like the question, this kind of effect for a long time, right? And also indicates that the spatial multiplexing can be used even without rich scattering, right? So even without rich scattering, we can get, which is a major benefit of the NFC, near field communications, right? So which means that even if it's just a point-to-point like the communication, we do not consider the scattering, we can get maybe 100 DF like increasement. It's still very like the exciting point, right? So this is the case, right? But today my topic is not near field communication. My topic is like near field sensing, right? So let's see what is like near field communication in a more detailed way. So what's the difference, right? So if you talk about this kind of far field like the communication, it's more like the beam steering, right? So this is more like this is like the flashlight. It's like the flashlight, right? And if this user is a near field communication, if this user we are moving, and this like the beam, like the moves according to the direction, right? And then if we are doing this kind of near field communication, it's more like the near field beam focusing, right? So this is more like spotlight, right? So when I'm working here, this spotlight and follow me, we can do the beam focusing. This is a key difference. Right? And then, okay, so in that case, we got additional domain to play with, which is called the distance domain. Yeah, you can just imagine this is a water wave, right? So there is a peak, there is a low point, right? So this is why we have this additional domain, right? So in that case, we got a lot of research opportunities. Right? Just like normal, we got additional like the power domain. That's also we are working with a long time with Zhiguo, right? So this is a very exciting point, right? We got some new things to play with. So as I mentioned, so when we move to this kind of nice, we give this kind of from near field communication to the near field sensing, nice, right? Again, it's a very easy to remember name, right? And so last year, so I was last couple of years, I did like maybe plenty of like I have talks, maybe up to maybe 50 like talks, right, in different places. And when audience asked me, Yue, so I know that what's the advantages of the near field communications. I just have one question. What is the disadvantage of near field communications? Right? So this is a very good question, right? Nothing is perfect. Every coin has its two sides, right? So I would like to see the disadvantage of near field communication is that it brings a large overhead. Right? So we have higher frequencies and larger antennas, right? Which means that if we do the antenna estimation, do the beam training, we have large overhead, right? Which increases the complexity, right? But this is bad. This is the disadvantage for near field communication. This is the good thing for the near field sensing. Right? Because for sensing, when we move a bit, right, and so when we, for example, use high frequency, large antenna, and you move a little bit, then it makes the sensing more sensitive. So this is the good thing for the near field sensing. That's why I moved to this direction. So I will skip this kind of something like the basics. So for example, this is for the single antenna sensing. If we do a single antenna sensing, this is say send this like the signal, and we got this cycle. And in that case, we can get this radial velocity. Remember this keyword, radial velocity. I will explain why we need that. And then if we move to the multi-antenna, right, we got additional. We can have the radial velocity and also the angle. Right, so we can get from this multi-antenna, compare the multi-antenna and the single antenna, we got additional like angle information. Now we can get angle, range, and the radial velocity. This is for the conventional multi-antenna far field sensing. Right. So now let's see, take another way from the signal processing perspective. If you do the Fourier transform from time domain to the frequency domain, right? So what we can obtain? Now this is, for example, this is the target like the parameters. Now we have this kind of import takeaway. For distance, if we observe from different frequency, actually it is essentially the bandwidth. And for the angle, actually if we observe from a different like antenna end, actually it's array size. And for the velocity, if we observe from different time, actually it's time length. Right? So the important takeaway is that this has the Fourier sensing resolution for the distance, angle, and the velocity are determined by the bandwidth, number of antennas, and the time interval, respectively. This is the case. Right? So now let's move a bit further to see how to model this one. So what is nice, and you know, if you're familiar with my research, usually I do this kind of what is nice, what, why, and how. Right? So now let's see how to model this kind of nice, right? So the near-field communication and near-field sensing, they can share the same like this kind of model, right? So we have the UPW, which is short for this kind of uniform planar wave, and this is for the near-field uniform spherical wave, and the USW, and also we propose a more general model. I will explain why we propose that one. Yeah. So this is for the we share the same one. So this is for linear case. This is for near-field modeling, and actually this is for the UPA. This is for this kind of two-dimensional. So this is for the UPA case. We got the additional like the red dimension for this. Yeah. So this is the modeling. And then let's see what kind of takeaway we can obtain, right? So actually, so we do this kind of performance analysis for the near field, for this kind of near field sensing, right? We got this kind of called the sensing network information, and we give this a sensing rate. So what is sensing rate? Why do we need to define this sensing rate? Actually, I'm quite proud of this work. So we try to use this kind of channel theory to analyze the sensing ability, right? So if you talk about this kind of for communication system, so actually we have this kind of the array gain, this diversity order, is a power scalar, right? So no matter you do this, you just talk about this kind of thing. You know, okay, this is how good your performance analysis is, this communication. But for sensing, if you talk this, the common bound is 0.1. Right? So you have nothing like direct sense to what is how the system is good or not, right? So that's the reason we develop this sensing rate, right? And actually we put this performance limit for this nice, and we got this kind of we want to get this kind of bound. Yeah, this is the case. And then, so I talk a little bit for our general model. Why we propose this general model? Previously, when we talk about wireless communication, usually we focus on this free space path loss. We do not consider this effective aperture loss, the polarization loss. Right? So what is this kind of effective aperture loss? Right? I'll give you an example. If you go to a cinema, right, you're sitting in the front, in the first row, right? You look at this screen. You cannot get the full picture, right? You need to watch like this. Right? So that's why. So this is called actually the aperture loss. Right? Imagine you are like this kind of scatter. Right? You cannot scatter the whole room. You just scatter this part. So this is why for a long time people ignore this point. Right? And actually we just look a bit further to see this kind of thing. This is AUSW, this is UPW. We can see the scattering law for the UPW and the AUSW there actually is log n. Log n, what does that mean? Log n means that if n is number of antennas, if you have 100 antennas, log n is 10. Right? And which means that if you have 1 watt to transmit, as a receiver, you receive 10 watts, ideally. But it's not true, right? So it validates the energy conservation law, right? This is because we are not using the correct model. That's why we propose this new model. We demonstrate that we also mathematically prove that it can satisfy with this kind of energy conservation law, right? So first we need the correct model, right? And now let's see this kind of why we need this kind of near field sensing, right? So now this is the key point. Well, what's the difference between the far field sensing and near field sensing? For far field sensing, actually, so this is the case I have mentioned. We got this kind of distance, the angle, and also the radio velocity. But for near field, the difference is that the distance and angle they couple together, which means that it is more sensitive. Right? This is a good point. And second thing is that they have the additional velocity called the transverse velocity. right? So previously we only have this kind of radial velocity. Radial velocity means that if the user is working like this, from this point you see, okay, this is static, because you only have this kind of radial velocity. But if you have the transverse, you can get more like accurate velocity, right? So now let's move enable the sensing in the spatial domain, so we can see the how. This is a very good result we have now. We saw this one near field means wideband. What does that mean? So actually, we can do some trading between the bandwidth and the array size. Right? Previously, we do this kind of sensing, we heavily rely on this kind of bandwidth. Right? For example, if we need a large bandwidth to help us to do this sensing. Right? But now, at some scenarios, we cannot have very large bandwidth. Right? So in this case, we can use the large array to replace this bandwidth, do some trading. Or theoretically speaking, you can see we have the large array size plus narrow band is equivalent to the small array size to the large bandwidth. Yeah, so this is we can do this kind of trading. So now, okay, so and for the near field, we can get this is the far field, we can only get this angle information. And this is for the near field, we can get exactly the distance and the angle information. Right? So this is the difference. Right? So now, and also we have this kind of large array size and this kind of large bandwidth. So what we can do, of course, we have this kind of thing. Yeah, I will ignore this kind of. I will skip this kind of the details. So we got this some very clear and tidy results, right? So for the asymptotic, for this cover band, for the wideband nice, right? For whether n is equal to infinity, whether m is equal to actually m is the array number of the antennas, and also the infinite difference distance, or the infinite subcarriers, is the bandwidth. So we got some very clear and tidy results. I will skip this. Yeah, and then we got some this result is I feel very excited. Right? You can see this is the trading. You can regard this kind of this is number of subcarriers, or you can see this bandwidth. This is number of antennas. Right? So this is more we can do some trading between the bandwidth and the array size. Right? So which means that this is okay, similar to the weight region or capacity region. Right? So you can see this one, this A is equal to 250, A is number of antennas, M is subcarriers. Right? So you can see 256 and this N and M is equal to 1, and they have the same performance and A is equal and with this value. So this is the case. Right? So we can do some trading with that. Yeah. And now let's see how can we use that. So what's the application scenario? Let's talk about this, right? So we can see this. Okay, this is the target. Now we have this kind of array size, right? So we got this kind of velocity projection of this radial velocity. For far field, we only have this radial velocity. But for near field, we have this additional transverse velocity, which means that the free motion of this user can be estimated. So if we talk about previous case, when we choose this kind of user's full motion, right, we heavily rely on this kind of camera, this kind of thing. But actually, the wireless signal itself is very powerful. We can use that. Right? Because previously, but we cannot do that because previously we do not really focus on this kind of a spherical wave. We say, okay, this is just a planar wave, but it's not. All the waves are planar waves, right? So we ignore this kind of benefits, right? So in that case, we got this kind of near field velocity sensing and do the pre-active beamforming, right? So if we go back to this previous millimeter wave communication, we do some beam tracking, beam sweeping, this kind of thing. Actually, for the near field, so we do not need the channel estimation. This is the first point, right? Because I mentioned a lot for near field communication, we have larger antenna size, larger the very high frequency, which increase a lot for this kind of channel estimation burden. But now we don't need that. Right? We can use the predicted distance angle to design the beamformer. This is a key point, right? Very attractive. And also we do not need the prior knowledge for the motion of the model, right? So if we do some prior analysis, previously we use some random walk model, this kind of model, but now we can know the really full motion state model can be estimated with nice. Right? Another thing is that if we do this kind of localization, right? So for outdoor localization, we can use this kind of, for example, GPS. We heavily rely on this. But for the indoor, it's not that accurate for the GPS, doesn't work. But in that case, for example, in this rotunda, we can use this kind of light to do the localization, and for the parking, this kind of thing. So this is quite exciting point for the application. And we can see, so for this kind of predicted trajectory, we can use the lights to do the trajectory prediction. And now we can get very accurate trajectory prediction. Right? So suppose that you are the moving user, like so. This is very exciting. So you can, for example, you can use it for the vehicular communications, for the UAV communications, also for this kind of HAPS, this as like Halim said. So it's just a lot of application scenarios. As well as you are moving, we got some like benefits, right? And some, of course, this is a very like the initial point. We still have a lot of like the direction to work on, and we can see, especially for the indoor localization, as I mentioned, and for the nights we can do the raise stars and with SIM, and Michael mentioned that, and hologram memo, and the linear set, and also for the continual itineraries is another direction I will push. I will present this during the GlobeCon, yeah. And in the captain, yes, and also other engineers with ISAC, yes, and the FAI is working on this, and so we still have a lot of opportunity to work. So every time I would like to acknowledge my team member, right? So because this is not my own work, it's a lot, right? So because I have another team, now all of them are in Creamery, so only myself is in Hong Kong. So I'm like a single person there, and yeah, and because of them, so I can make it. Yeah, thank you. And if I have any questions, I'm happy to do the job. Thank you.
Okay, see, we have one question, short question, yes, please.
Presented signal model is formulated for the system model with linear, planar, uniform antenna array. But it can be generalized for any geometry, for volume geometry with non-uniform antenna. What effect do you expect in such system model?
Yeah, this is a very good question. Yeah, so you are correct. Currently, we only have this kind of model. Yeah, so it's here. So first, we have this kind of linear array. Right, and then we have this UPI, right? But actually, if this is a kind of like the circular or the sparse, right? So we do need some. But the model is more or less the same from this fundamental perspective. They are the same, right? But of course, this kind of equations, the distance is not the same, right? But which means that every model, for example, we have the circular array. You need to rederive this Rn, right? So this is the difference. Yeah.
Still vectors are different.
Yes, this array. Yeah, so this array is different. Yeah, exactly. Yeah, yeah.
We try to look at it for spherical antennas also.
Yeah, spherical antenna. Yeah.
That radiate also the near far, and at the end you will see that you cannot play with all the tilts to get the high capacity. There is a small match, and this also the far field and the near field is completely different from this kind of antenna. We try to solve this also.
Yes,
so it has another. I mean, you have to consider others elements.
Exactly.
Okay, thank you. So time for lunch, but we have that you have to back at 3 p.m. Thank you so much for the next session of the keynote speech.
Thank you.
So much.
Thank you. Yeah, okay, this one. Yeah.
Thank you so much.
Thank you. Thank you.
the application for 6G, right? So maybe we're talking about the immersive experience. So, so this picture is kind of some imagination about, how the future, this surreality, the mix of virtual and digital, physical and digital world together would look like. So we can see that maybe you see with your augmented reality glasses, you will see these, whales and fishes swimming in the street, or maybe Abu Dhabi, or Dubai, or Hong Kong, right? So metaverse actually been talking about the last few years. It was very hot in 2021, but then Facebook changed the name to Meta, then slightly getting down. So, and of course ChatGPT comes as well. But still, we have doing research, in the past, like maybe called virtual reality, augmented reality, or extended reality, etc., etc. So basically, the technology to bring immersiveness to our daily life can be, we go to a totally virtual world, or you just stay in the real physical world, and we bring the digital content to you, right? But the key, the world metaverse actually came quite a long time ago, was from this Neil Stephenson's science fiction Snow Crash, right? Was published in 1992, so over 30 years ago. And it described this virtual world, right? So that world described in this sci-fi was it's totally virtual, right? So basically you have to put in your virtual reality headset, whatever, then you go into this totally virtual world, you have your avatar is going to talk to other people's avatar, right? So, you can do all kind of activity that you can perform in the real world in the metaverse as well. So this is a version of like totally virtual metaverse, right? That the version that maybe Mark Zuckerberg, the people who focus on virtual reality would like. But today we're going to talk more about how to bring the digital to the physical world. But at least you get the picture here. So this actually, we envision that maybe metaverse is going to bring us some kind of different paradigm change. So the left one, this long time ago, right? That at the beginning of the internet, they say, okay, on the internet, nobody knows that you are a dog, right? So basically, the motorist of usage of internet. On the right, that I put the picture there is in the metaverse, you can be a cat. So basically, that you can. The new paradigm that you can actually live a completely different life in the metaverse. If you want to be a cat, then you can behave like a cat, right? So nobody would know that you can choose a completely different life. Of course, there are some problem people raise up, about identity, about community, about some kind of social perspective that may raise up in this kind of scenario over there. So then how it related, right? So I say the future of the internet is 3D. So basically we are looking today at a 2D screen. I'm still looking at a 3D screen, right? But our world is three-dimensional. So how this metaverse scenario is going to actually bring the internet to 3D, actually maybe 4D, 5D, you get in like, smells and different kind of things, so you can make the internet even haptic, right? So you can be a 4D, at least 3D in this case. Okay, so this is a kind of reality, virtual reality continuum. So we see from here, so basically the left side is the physical reality, right? So we assume that what we see is reality, right? Of course, it may be just a simulation as well. And the right side is a virtual reality. And then when we move from the physical reality to the virtual reality, means you're adding virtual content into a physical world, right? And in the middle, there's augmented reality, which a mix of the physical world and digital world together, right? So the more digital content you add, that you move more to the virtual reality side. And when you go to virtual reality, that you don't see the reality, right? You don't see the physical world. You just totally enter a digital realm, which is maybe the metaverse, okay? But I mentioned that my version of metaverse is less, dystopian than maybe Zuckerberg's version. That actually, I'm more looking from the background of augmented reality. I would like more bringing the digital content to our physical world and make our physical life better. That maybe also the application that you can have for this 6G in the future as well. That you bring a lot of high quality digital content to our life. So people talk about how to build a metaverse. So basically talk about physical world in the left, the digital twin, which are can be a digital model of the physical world, right? And then the right side is kind of, maybe the metaverse that I described, a mix of the physical and digital. So digital twin, I think we have many speakers talk about digital twin as well. So basically, you basically you build a metaverse can be a model. You build a model of the physical world first, right? So basically, you have this, property of the physical world that you want to capture, and of course, you don't need to model everything, right? The digital twin, you just interested into about the temperature of this room, that actually you just need to capture about some property which is related to temperature, right? But the connection that's supposed to be the digital twin and the physical twin, there will be a connection by data, right? So the digital twin change, the physical twin also make some change, and then the vice versa, right? So this is the first step that if you want to bring the physical world into merge together with digital, right? Then you build digital twin. But of course, in the metaverse, there are a lot of things which does not exist in the physical world, right? So it does not have a corresponding physical twin in the daily life. Then this part actually much more content actually does not exist, right? So we call digital native. So digital native are the things that only exist in the digital world. They don't exist in the physical world, right? And digital native usually result from the content creation. So basically, we create the content. It can be some content creator, artists, maybe create some art, digital art, right? And then they put them into this. Okay, I would say that such digital creation can be distinguished from the physical counterpart, right? Or only exists in the digital world. And the content creation, basically, we expect is going to create a lot of economic activity, right? So basically, the current problem with maybe the hype of metaverse a few years ago was actually the content. There's not enough content creation at the moment, right? That you may go to some metaverse, like called metaverse, and they stay there maybe half an hour. You find that you have finished consume all the contents over there, right? So then the content creation is very important, but you need the content creators to get some financial benefit by doing this, right? So you need kind of, some kind of digital economy to push this economic activity. And we say the metaverse will be, adding the digital twin together with the digital native. So basically, we hope it exists as a self-sustaining and a persistent virtual world that we coexist and interact with the physical world with some high level of dependency. And of course, ideally that you will be able to support unlimited number of concurrent users, right? Of course, that it depends on the network, depends on the computational power that you can secure for this purpose. Okay, so this is kind of, but just, in my vision from this augmented reality, so I kind of calling this metaverse as a surreality. So basically we say that we envision in the future that the virtual world will be coexist with the physical world in a very immersive way that we cannot distinguish actually what is real and what is virtual, right? So basically, especially you see a lot of digital content actually appear, showing up your daily life, actually you get used to them. So basically the future that will live together with your digital object, digital content. And you see them, maybe I don't need to come here to give a talk, right? I just send my avatar to come here and then give a talk on behalf of me as a holographic display over there, right? And this real reality we call surreality. And there's also opportunity over there that we will here. I also introduced a concept called meta formation. So basically, we find it still very difficult to create for companies to create augmented reality app that, even a small, maybe a small shop or restaurant want to create a AR application, I need to actually pay quite a lot of money over there because it involves, some kind of pipeline of doing this 3D scanning or, doing content generations and then, recognition kind of, context-aware things, right, that actually is quite tedious to do. So the concept of meta formation is like coming from the terraformation that basically the terraformation is trying to change a planet to be like Earth-like, right? That, and, this Earth-like species can live over there, right? And the meta formation from the concept that how can we actually easily change this physical space into a metaverse space that digital native actually can easily live over there. So it's just a kind of process, standard process to create this. And we hope this is actually going to create a lot of commercial opportunity as well, that you can be easily deploy your digital object here, right? That we can see whatever you display over there, that actually is a good opportunity over there. So this is some kind of thing that we propose to do. Maybe for example, bring Northern Line to Hong Kong, right? That basically you go to of course there's no snow or no Northern Line in Hong Kong, but you can use this kind of AR technology that you can see the Northern Line in Hong Kong. This is another concept that we're trying to do with the shopping mall over there. So basically, you go to the shopping mall, the Dubai Mall, maybe Abu Dhabi as well, they have a nice shopping mall, but we can add in the digital element, virtual things over there as well. Right? Besides seeing the physical mall, you can see also, like digital art over there. You can, see them with your smartphone or smart glasses, and actually aim to improve your shopping experience. And this is also some kind of surreality concept for like concert or even football match, for example, that you're going to host maybe some kind of big event, right? That is, besides seeing this performance over there, we can add in this digital effect, right? So this actually you see them, in the three-dimensional way that actually give you a better experience over there. So where are we now? Actually, the metaverse kind of chronicle actually things start quite many years ago. I mean, even 70s, people are talking about some virtual world that, you can go there and, you can have a different kind of life in the virtual world, right? But that it starts from science fiction book, and they move from, for example, text-based interactive game, right? At the beginning, there was no graphical, computer graphic, so everything is just text-based, and then virtual open world, massive multiplayer online game, right? But you can see that, with all this technology coming, with the computer graphic, with the massive internet, with the touchscreen, crypto, AR, VR, actually, it moved actually to form what we have today, right? That you have actually people use cryptocurrency to secure this ownership of the digital creation, right? That you can, at least you can show that you own this kind of digital content, that otherwise, people just copy and paste it, do a screenshot, and your pixel just be stolen, right? So that's, it's a way, actually crypto is the way to motivate the content creator to create content. Okay, so obviously we say that technology is the way, the catalyst to drive such transitions. And this is actually, some people may ask actually what this metaverse or AR, VR is going to bring to the landscape of today's app as well, right? So you can see that we're actually putting quite a lot of the current app you have on your phone or your computer and then do some kind of categorize them. So move from the left to the right, you have increase in the the richness of the content, right? So basically from text and a picture actually equal to 1,000 words, and they have the audio, have the video, and of course our physical world have the richest, content, right? And so we can see that move this side, you can categorize your app in the way. And from the bottom to the up, actually there's improve in your user's experience or your engagement in this content, right? So you can see that for example Zoom, you watching my video from Zoom, that everyone have the same experience, right? That, you don't have any personalization over there, right? But you move up from, you can see that Netflix, you have personalization, right? That you're going to recommend the content based on previous watching behavior. So you personalize to what you like, right? But then Netflix actually does not allow users to get engaged to produce their own content, right? So no user-generated content. But then YouTube actually allow the users to get into this community and also produce their own content. But in the other way, like the TikTok actually provide better social, community activities. So you can go up over there. And we see that actually metaverse is going to bring us two things. Like one is security. So basically when you make an app in the future, you need to consider both the physical world and digital world and how they merge together. So basically give you one more dimension to create your application, right? And the top is also about perpetual, right? So basically it's things archiving, right? So you build an art, physical art, right? Then you can put the art into a museum, right? And actually, in the future, many of the art form will be in a digital way, right? So how actually you archive this digital creation, right? So these things that also we need to think about in the future when we make things, okay? Yes, in order to build the metaverse, we need a lot of technology. So we need, for example, network, right? We need the network technology. We need maybe edge cloud computing, because when you talk about latency, that you need probably or computational power, you need cloud, right? And AI is going to play a key role. Going to briefly talk about how AI is used to create the content for AI, for metaverse, and then computer vision for recognizing the scene, right? To do all this face recognition as well. And then blockchain technology for the ownership of your digital creations, and of course, user interactivity and extended reality, maybe AR, augmented reality, virtual reality. They are the gateway to get into a metaverse, no matter whether it's a totally virtual one or a physical digital one, right? And assume that we have all the technology, we're able to build this metaverse as a platform, a software platform over there. But it's still not the end of the story, because we mentioned about that you want this metaverse to be able to sustain it, right? That be able to coexist with the physical world. That means that actually you need an ecosystem to keep things running, and the ecosystem actually you call the lower egg pillars as a hard technology, that you need the soft technologies to keep the ecosystem running. So basically, for example, avatar, how to make your avatar, right? Should your avatar look like you? Or can your avatar maybe, normal people's avatar maybe is just 2 meters tall. So your avatar is like 200 meters taller than others, right? So these things you also need to think about. And the content creation, who is going to create the content, and how the content is going to manage, and what kind of virtual economy is to support this system running. Of course, whether it's socially acceptable or not, right? Maybe in some country you have to behave in certain way that to be socially acceptable, right? So those things in the metaverse can be crossed. Maybe say the future internet, right? That each country may have different kinds of social norm that you have to follow, right? So those things actually security, privacy as well. So those are the things they also need to work on to secure this ecosystem. So this actually, I put everything here, right? So you have the network is very important. That is kind of supporting everything about, right? Especially talk about maybe we need a lot of bandwidth, or we need very low latency for this. Okay, and then there's things going up, right? So this actually I already mentioned. I'm not going to take you so much. So there's actually a lot of research questions. You really want to build things, right? So for example, these are some of these research problems that I think is still need to address. For example, even like maybe network, right? So of course there's 6G over there. There's some kind of network-aware applications, for example, AI. What about automated digital twin creation? What kind of computer agent is going to help you to be the NPC to maintain the metaverse operation, right? Avatar, for example, the appearance and design, what is human avatar interaction, maybe robotic area as well. So there's actually a lot of opportunity for 6G and also for networking or communication researchers over there. So some example here, I've already mentioned about this, virtuality continuum, right? So we can see it over there. So today, actually, virtual reality headsets are quite cheap, right? They're not expensive. And actually, the quality is pretty good. So I don't know how many of you have been playing with the VR games, but besides game, right? So my background, I was originally doing networking communication, but the past, 12, 13 years, I'm mainly working on AR, VR, and the recent years also doing joined the Department of Computational Media and Art. So we have actually a lot of art students, art faculties, go more high level stuff like content creation. So you can see that actually the artists have been used VR quite a lot for example, painting. Right, so it's actually they find it to be very useful when you do the painting on the physical wall. Usually, do the painting maybe on a canvas, right, or paper. So it's a 2D, right? A canvas or paper or table is 2D. But the artists actually these days they want to do 3D painting. So how do you play 3D in a physical wall? Is you can do it, but you become a sculpture, right? So you can. But in VR, actually, you can do a painting in 3D because you do it, just draw everything in a 3D way, and they actually be able to save in 3D and buy and sell them, right? So I saw that some of our students actually do a 3D painting and put it on NFT to sell, maybe $7,000 or $8,000 for some of this normal creating, right? And actually also allow actually a lot of people to do the co-creation at the same time, right? So basically, a group of artists actually they doing the art creation together because VR actually allow them. Actually, now they're in the same room, but actually they don't necessarily to be in the same room, right? Because they can just put on the headset and then their avatar come here, and the avatar actually do the creation together, and because it allow actually a real-time interaction, right? So basically you can everybody together and do this creation at the same time. Of course, at the COVID time, there's a lot of people using virtual reality for teaching, for maybe for meetings, right? So these are examples over there. And for the AR aspect, right, that people use maybe Pokemon Go was a long time, but there's also some other augmented reality app today available. For some of the IKEA app actually allow you to do to see how the furniture will fit into your room, right? Basically, you download the app or the IKEA furniture. Actually, you can try to put some furniture into your physical room and see how it fit over there, right? And there's AR glasses also get cheaper, right? That major players or actually some company, maybe Vision Pro, which some of you may have used today, this year from Apple, is actually quite good experience, but just more expensive, right? There's many companies, for example, in China, they're making cheaper device, but also quite good quality that can easily affordable. So, but there are also challenges over there. So this actually may be a more technical slide, one of the only little bit more technical slide here. So it explains how actually AR works, right? So this is just one scenario. So augmented reality, usually we think about, there'll be, you have a camera, the camera is, recognize the environment, and then you go in somewhere to get the digital content and put the digital content over this environment to augment it, the reality over there. Right? Of course, this is the common way of thinking, but it does not need to be augmented with the visual. Like can actually augment it with the audio as well. That you detect the environment, and that your speaker is going to make some music to augment your reality here. So, but of course, this is a more common way. So, so the pipeline usually like this, right? You've got a frame or picture coming in from the camera, and then you do object detection from this video frame, which can be just a picture or a pixel over there, right? And then you do feature extractions from these pictures of video frame, and then you do object recognition. You see, what are the objects over there, right? And then you do you go to a database, get the you recognize that this is a person, his name is whatever. You want to get his education background as well, and you go to database and get them. Then you do the template matching, and finally you do this annotation rendering. Right? Then now I got the information about like these people, and I display over there. So this process actually this whole pipeline. You are supposed to be, if you want to do it in real time, you need to do it at least 30 frames per second, right? So basically you need to do it around 30 milliseconds. You want to do the whole pipeline have to be done in 30 milliseconds, right? So there's actually involved a lot of computational heavy tasks, for example, that object recognition can take sometimes. Even itself can be more than 30 milliseconds to compute, right? And so that's why actually people are talking about using edge computing to do this. Basically, you reduce the latency or put in the GPU close to you to do computing. So the A2A latency in VR, as I mentioned, that today quite many of these apps or research systems that people publish take around 280 milliseconds. So it's actually quite slow. We are talking about real time. And of course, the network transfer take around, they assume that the network transfer is like 50 milliseconds, which is reasonable, consider that it may be running somewhere. Then actually, it only takes about 18% of this, the total latency of the pipeline, right? So a lot of actually the latencies, of course, you can use more and more powerful GPU to accelerate, right? But a lot of the latency actually can be due to the computer vision part, right? For example, we say object recognition, object feature extraction, those take actually a long time. So you want to do 30 milliseconds, you need to, of course, compress the network, right? You maybe invent some faster transfer, and you also want to maybe reduce the computational time. Then you actually see whether you can push it lower, right? And for VR as well, so basically virtual reality, there's also problem today, also related to network, is that so people usually feel dizzy with VR for too long. And one of the reasons, of course, is because our body structure, that what you hear and what you see, actually, they're not consistent, right? You saw that you're moving, but your ear actually tell you that you are not moving. So usually, you feel sick, right? And when you feel sick, you may vomit. The reason, because our evolution, right, that when you feel sick, because you are eating poison food, right? So the way is to fall out to save you. But another reason is because the pixel is the resolution too low, right? The resolution, if you want to match the normal eye resolution of 2020, right, eyesight, you need actually 3,600 pixels per 1 degree area, right? So you do a 600 degree video, basically you need 16K resolutions for this. And 16K actually it also causes problem for network transfer, right? Maybe you get 300 megabit per second if you are transferring 16K video, for example, here, right? And you can do it, of course, now with maybe Wi-Fi, with maybe future 6G, you can do it. But then at the moment, there's also decoding problem that you can, quite a lot of the device, actually, none of the device you have today can decode 16K video, right? You can have maybe a GPU as edge server to do the decoding, but yeah, but you have to do things, right? So these, okay, so of course, I heard today a lot about, holographic beamforming. I saw it's talking about holography, but it's not, right? So, but in the future now, the display should be also there's involvement. So this actually this is hologram. So this is really hologram, but they are very, very small, and they're using laser. And the size actually is quite. This is a fingertip, and the hologram actually is over there. Is quite small. But there's new technology, actually, you can use it to mimic some of this holographic display, but that would be useful to save my avatar and have a holographic display over there to give my talk. Okay, so I think I have 12 minutes more, so let me skip some of the slides to control this time. So, metaverse, there are a lot of things to happen, maybe about user interactivity, how do you actually input tests in the metaverse, how do you interact with the content or avatar, how will you shake other people's hand in the metaverse, right? So those involve a lot of interactions. And there's challenge of today's headset as well. Usually, the field of view is quite small. So basically, when you make your app, you need to make sure that you are not displaying too much content at the same time. So you need to have better AI to predict what thing to recommend to the user, right? And there's a lot of interconnectivity with the IoT, with the connected vehicle, with the robotics over there. And for example, that people might talking about how actually people be able to interact with the robot, that you can actually train the people in the metaverse to interact with the robot, right? So here, AI actually, of course, the core of one of these one of the core topic of this summit is about the AI, right? So here, when ChatGPT comes, actually the hype in metaverse has dropped a lot, right? But then we see actually opportunity with the AI that actually can help a lot about metaverse advancement. For example, they can help with the avatar creation, be the artificial agent and NPC in the metaverse. They can help with the content creation. AI can also create a virtual world itself, right? And solve a lot of personalization problems that I mentioned. So this shows you how the avatar can be created with the AI, that you just upload your picture, and then they can create an avatar pretty much look like you. And this actually. One of our work, actually, we used AI to create the whole virtual world. So basically, you see this video is actually all created with the AIGC, right? So basically, you just give a prompt, and then it actually is going to, for example, to create this 360-degree video, right? So let's start with our exploration over there. And so basically, you say that you want to be the movie of Star Wars, right? And then this actually generated, okay? And it's not like a mid-journey type of thing. We actually generate thing not as a picture, but we generate the source code itself. Because source code actually you have better control of what actually to add, what to move, right? So this is actually generated with Titanic, right? So this actually is 360-degree wall is created with just the AI, right? So then you want to go to another movie, right? You come here and you see the airplanes actually can even fly, right, over there, right? So these are all just created with the AI. And it saves a lot of time, right? To ask my student or ask some artists to view this virtual world, it takes time and take money, right? But what we did here is just, you just give 2 minutes of time, and then it's going to generate for you. You know how to do it, right? Okay, so this digital heritage, there's a lot of privacy issues in the future as well that we're going to face. For example, and there's also social acceptability factors, and we're talking about, like people talk about, for example, virtual immortality, digital immortality. Here the Times magazine say 2045, the year the man will become immortal, right? So basically talking about how to build your digital copy in the digital world, right? And again, privacy here is get tricky. That sometimes in our daily life, we know that maybe somebody next to me, I don't talk to each other, talk about secret, but in the metaverse, another person can be just a rubbish bin, right? You cannot tell whether this is an avatar of a user or just a regular rubbish bin, okay? And some more scary thing is like spending 20 minutes in the VR simulation will leave just under 2 million unique recording of your body language, right? So there's actually a lot of issues over there. And who is going to govern the metaverse and code and rules, how this is going to. So I'm another 6 minutes. So basically I show you some of these projects that we are doing. So basically we build this, we have 2 campuses now, one in Hong Kong and one in Guangzhou. So basically our project is to build this metaverse to connect 2 campuses together for teaching, learning, as well as also research. So this video showing these 2 campuses, right? So this is just a demo. It's not the illustration about these 2 campuses. And actually, during the COVID time, this was not possible to travel between Hong Kong and mainland China, right? So basically, the concept was to build this 2 virtual world, this platform, and for students be able to come to visit another campus, right? So this is another work that we have is about, I talk about meta formation, about scanning the whole environment, right? So this is actually a SIGVAL papers about how to actually scan the environment and create a digital twin quite easily with the monographic, just one single camera. And also, of course, with the innovation of this one is also we add in some inertia sensor. Actually, you can detect the terrain as well. That, you do the SLAM scanning, right? You just scan this environment, you just get this, you just get this image, but does not give you the tall, the high, the terrain variation, right? But with the combination of both the camera and also the inertia sensor, actually we can build the terrain variation of this environment as well. And this is another artwork that we created for this. We call it the Garden of Coexistence. So basically all these flowers are generated with the AI, and then we add into our university campus, right? Basically, you go around with your headset of your iPad or your phone, and you see these digital flowers, with intentionally to make them with the Gaussian spotting, so it does not look like a real, like a physical flower, but actually adding some more magic over there. So then, the metaverse classroom we created to connect to campus teaching over there. So this physical classroom in Guangzhou, and then last semester, fall 2023, we have this teaching, this lecture actually. Have 10 students in Hong Kong, 10 students in Guangzhou join these lectures with a headset, right? And you can see that some students actually is normal behavior of the student in the classroom. This is the Hong Kong campus, and that one is in the Guangzhou campus. And this actually, so basically, this the classroom look like. So we build everything from scratch. So basically, we have designers, and we build this classroom as a spaceship in the air. So the red bird is HKUST logo, so it's flying over there. And the student actually can choose their own avatar and upload their picture, create their own avatar. And then we have the lecturers over there. So, these have this display over there. And this, we have the control panel, which can control the slide to, the presentation, right? So basically, they are views. And this actually is student view, so how the student actually go attend the lecture, right? So each student actually, two students, this course called design thinking, basically two students from Hong Kong, 2 students from Guangzhou, they work as a group to do a design project. So suppose normally you need, for design thinking course, you need 4 people sitting on the same table, so you can make some stuff, together over there, right? But it's not possible if you are 2 locations. But with this class, with the virtual, environment, actually they can sit together in the virtual space and do all the design. And these are all built with the tools, whiteboard editing tool. And when you make change, actually they change. We add the function that the PPT will change with your view, right? And so basically each group have their desk table, and they sit together over there, and also have their own group display over there. And here, you see that actually this design course, right, so be able to actually pick up all this, these cubes and spheres, and even build a spaghetti tower challenge over there. Okay, so this actually was done last fall 2023, and then spring 2024. Actually, we add in more elements. So basically, maybe after hear me another half an hour, you get bored with me, right? So my students actually have the same experience, right? So how could we do with this? So before they get bored with me, so I invite I make the AI lectures, so they would come and teach some of my lectures for me, and then coming back, right? So these are the AI lectures actually.
Welcome to the future of learning.
So this is as well as students from both campus join together, and quite a lot of time they just come to virtual classroom, right? And so this is my kind of avatar, which one of the versions of the avatar which is not super nice, but Einstein avatar, right? So basically, we get them to teach part of my lecture. So it was actually the teachers. I have like 10 teachers created with different kind of versions. So myself, this one look more like me. This is actually also a digital me. And then there's different kind of teacher from different background, right? For example, and give different lectures and different colors and different style, cartoonish or photorealistic style, right? So all this. We also have like idol area, which is the virtually created character who also only live in a virtual world. And then we have Einstein as well. So basically, yeah, this is in the VR, right? So each person can see their personalized digital teacher. I like my teacher to be like a cartoonish person like this one, right? Basically, you can choose your teacher, and then you see this on your headset, right? And then we also have, like for the right-hand side, it's better I be able to control this video, right? I can jump it, but since the control is somewhere else, so then I have Einstein as well. So you can see Einstein give you maybe physics lectures, right? So 3D Einstein, he's going to. The only thing that I'm not happy is about Einstein's accent. It's now very American, so we need to add some German accent in the future. But at least you can see them giving lectures over there. And yeah, and these are the teachers, right? That
Good afternoon, everyone.
we are like Diana, and then
digital guide for today's journey.
yeah, but
into the
they look
captivating
pretty
world of virtual
real,
reality,
right? Like
also known as VR.
better looking than me. So yeah, and then there's so basically each of them actually have one person and give a lecture. Like each class they only give 30 minutes because I don't want to be fired, right? They may say, okay, you don't give lecture yourself, so I just limit to 30 minutes per lectures. And the students like these two most. They don't like me so much, but they rank number 1 and number 2 of these two ladies. Yeah, and I think, the future, we hope that, with all this metaverse technology, not only about gaming, right, but how can we actually bring in to improve the future education, right? Maybe, with the MOOC, today you need to spend a lot of time to create the content of the MOOC, right? Maybe we can just ask the AI to generate the content and give the lecture, right? Not me giving the lectures here, right? And, a lot of personalization, et cetera, et cetera. So I think time is up. Okay, thank you.
Okay, thank you so much, Professor Hungry. We have time for 1 or 2 questions. No questions? Okay, I have several questions, but I cannot monopolize this. So I see that metaverse, we were living a hype on that years ago, a couple of years ago, before. Right. And it looks like this is breaking a little bit. I would like, when you deploy this, of course, there is an infrastructure behind. Is it 5G? I mean, is it required to have, at least with good quality, something similar as the quality of 5G? I see the latency, so somehow it's a kind of science or technology that is dependent of others, which is the infrastructure. We were speaking about 6G. Latency would be something very critical. Maybe this is also a pipe to the evolution of, from point of view of latency. I see the video, compression of the video, making the adaptability between the latency and the quality of the decay. I see 16K, which is crazy for a telecom guy as me, okay? So I will not sleep this night about 16K, okay? Where is the pipe that can support this nowadays? Right. So what is for you really some of the real bottlenecks that if we solve this, we will get maybe the boom of the metaverse?
Oh, yeah, thank you for the question. Yeah, I think the technology, today is actually quite good already. Like maybe headset is low, 5G is helping a lot as well, as of course, and edge computing is also. So I think the current problem is the content. It's not the hardware or the network, because we don't have 16K at the moment, right, anyway. But the content is a problem that we need high quality content, right? Otherwise, people just go, I mentioned that people go to the metaverse and after 30 minutes, they get bored because there's not enough content for them, right? And I see that actually these content creation have been picked up this year. Then, companies start making, like VR experience room in different cities in China as well. And then And maybe they know that the content is going to be needed, right? Also for education content, right? That we're able to create more education content that people can go into, for example, go to Mars to study the astronomy, all this stuff, and actually would get it up quickly, yeah.
Okay, okay.
Okay, thank you.
Thank you so much. So I will request the applause for Professor Pan Hui. Thank you so much. So we move to the next keynote. So titled 3D Intelligent Meta Surfaces and Their Applications. Okay, we had, I think, a lot of sessions on metaverse and so on. This is quite hot topic, and I thank Professor Showing from Nanyang Technological University of Singapore about this talk. So just a few words about Professor Showing. He received his engineering and PhD degrees from Nanyang Technological University in Singapore in 2000 and 2004 respectively. He has a postdoc fellow with Lucent Technology Bell Labs, Murray Hill in 2005, and between 2006 and 10, he was with the Institute of the Infocom Research in Singapore, well now Institute. Since 2023, he has been with School of Engineering and Electrical Engineering of Nanyang University in Singapore. Of course, Dr. Yuan is received plenty of prizes, worldwide prizes, like the best tutorial paper 2024 from the Communication Society. Also, the Communication Society, Fred and LRCK Prize in 2023. Also, the Marconi Prize, prestigious Marconi Prize Paper Award in Wireless Communication 2021. And the IEEE IPB Outstanding Paper Award 2023. And also the RASIF Best Paper Award Journal on Wireless Communication. He's a fellow and also highly cited researchers by the Clarivate website, science website. Thank you so much, Professor Nim. I give you the floor, please. Go ahead. Thank you so much.
Yeah, thank you. Okay, thanks for the introduction and also the organizer to invited me to have this chance to share with you our research project. So I'm Chao Yuan here. So I'm from NTU Singapore. So I'm going to share with you about our recent work on the 3D intelligent meta surface and the applications. So some of the work are overlap with what Macro presented earlier just now, but I think this shows how important that we see about this topic and we are excited about this thing. Okay, so this is the outline. At first, I will give you some background about this so-called smart radio environment. Then we'll introduce you about two 3D architectures of the metasurface. One is the so-called state intelligent metasurface, which is a multi-layers metasurface structure. The other one is a flexible intelligent metasurface, which we call it FIM. Okay, this is the paper by Macro. He mentioned about this so-called smart radio environment. Okay, in the sense that in the past, what we did in the wireless is that we are trying to optimize both the transmitter and receivers. Okay, but later on we come up with this so-called concept of the smart environment, in the sense that if we can change the environment, then we can make the environment as part of the optimization parameters. We can jointly optimize the transmitter, receiver together with the environment. So how can we change the environment? One of the techniques is the metasurface. Okay, this metasurface, we can change the polarization of the radio wave, or we can do some kind of beamforming or scattering. So by doing so, we can make the environment to fit our wireless communication needs. And this technology has been listed, by many white papers as one of the promising technology in the 6G, and also this year listed as one of the emerging technology by the World Economic Forums. So let me share with you one of the prototype that we did in NTU with Professor Guan Yongliang. So over here you can see, okay, this board in the middle, this is the RIS, okay, this is the board we have. We are seeing the back side of it. So this is a 10 by 10 element RIS. So for this RIS, we designed for 10 gigahertz. Okay, so it's 10 by 10, and each element is 2 bits, so we have 2 bits of control. And over here, you can see this is a transmitter, and there's a receiver. So we are using a horn antenna, it's a directional antenna. And later you can see, without the RS, basically they are not able to form a communication link. Okay, and through the RS, later you can see we can find the best angle of reflection such that we can reflect the angle, the signal from the transmitter to the receivers. So over here, this is the computer showing the received signal. So we are sending a 16 QAM. So when the communication link is established, you'll see a clear 16 QAM over here. Okay, but when the link is lost, you can see something messy here. Let me play the video. Okay, so this is the transmitter, receiver, and the RS. So now it's perfect. When we move the receiver, you can see the link is lost. Okay, then the RS will start to reconfigure and we re-establish the link. When we move again, we'll start to reconfigure and then re-establish the link. Okay, so for the RS, we've seen this, has been in the past 3 or 4 years, which is quite, successful to some extent. Okay, so, but we are asking ourselves, what is next? After RS, what is next? Or what else can this meta surface do with us? So, early last year in 2023, we come up with some idea that, how about we can use this surface not just for communications, but can it help us to do some computation? Help us solve some problems, do some kind of processing, signal processing kind of tasks, or even classification kind of problems. Okay, we come up with this idea, and strictly speaking, by that time when we write this magazine, we have no idea how to realize it. We don't know how we can do it, or we just imagine, if this thing can happen, it will be good. So until recently, okay, we come out with this structure called the SIM, State Intelligent Meta Surface. So basically, is to have multiple layers of the RS. Okay, stack them together. Okay. However, unlike the RS mostly is for reflective. Okay, but for the SIM is transmissive, which means that the signal will pass through of it. Okay, so the signal will pass through first layer, second layer, third layer, and then going out, for example. Okay, and then later part of this presentation, we will also talk about the FIM, which is the flexible intelligent meta surface. Okay, so let's go into the SIM. So what is SIM? Okay, when we call this name, there are some meaning. Okay. So the stack basically means that the structure, it has a multiple layers, stack them together. So that's where the stack coming in. And later on you can see is that, in fact, this SIM mimic a neural network, which means that it's a neural network in the radio wave domain. Okay. Then second, intelligent in the sense that this thing is smart. Okay. It is mimic a neural network. It can solve many problems like a neural network. And finally, meta surface means that this thing is based on the metamaterial and it has the reconfigurable property in the sense that I can change it, I can reprogram it to do different functions and functionality. So how this thing is being used in real life? You just imagine that this SIM, right, is the layers that outside your base station antenna. Okay, so this is the RF chain coming. Okay, the RF chain here, there is a transmit antenna. So after the antenna, over this box here, there are a few layers of this meta surface, which is the SIM. This is how you can imagine how this thing being used in real life. In fact, what we want is to have this SIM to carry out various signal processing and computing tasks in the radio wave domain, in the analog domain. Okay, let's see how we can get this done. We use first problem we consider is the multi-user MIMO, okay, which everyone of us we are familiar with. Okay, so in this multi-user MIMO problems, let's come, a little bit of mathematics. Okay, let's assume that we have L layers of it. Okay, L layers of meta surface. So of course, L is a design parameter. We need to decide how many layers is needed, and there are n atoms, which means that every layer there are n number of atoms on this layer. Okay, then we are serving k users, and there are m RF chain. Okay, so what we try to do is that in the past we always do the beamforming, multi-user beamforming in the baseband. Okay, using the FPGA, the computer, to compute what should be the beamforming, the matrix. Okay, right now, what we try to do is that this beamforming matrix will be implemented using the SIM. Okay, let's see how it can be done. Okay, over here, the key equation is the equation 2. Okay, this G basically is the effective matrix of this SIM. Okay, what is this G? Okay, you can see it's the phase times W times another phase times W. So basically, it describes this device here. Okay, it's the phase times W, phase, then and W. So the W is the channel between the layers, okay, which we cannot change, okay. Over here, we use the equation 1, which is a near-field equation to model it, okay. This equation 1 is a strong assumption, okay. I just agree that it's a strong assumption. It may not be true, okay, but anyhow, we have to kickstart, okay. So let's assume equation 1 describes the channel. And what we can control is the phase of all the meta atoms on all the layers, okay. So if you're looking at this equation here, by changing the phase, if we have enough number of layers and enough number of atoms, basically we can get any G that we want, okay? Which means that if we have enough degree of freedom, okay, many layers and many atoms, we can adjust the phase to get any G that we want given the W, okay? Which means that we can do any beamforming that we want using this sim. Okay, so this is the idea behind it. With this in mind, then we can write down, what is the receive signal per user, what is the SINR per user, okay? With this formulated, then the next is just solve the mathematics problem, okay? So we can formulate a problem like we want to maximize the sum rate, 1 plus sum rate from 1 to k user log to 1 plus SNR, okay? Subject to some constraint, total power constraint, then the phase should be 0 to 2 pi. So we just need to find the phase on all the atoms, then we can solve this problem, and the beamforming is done. So we come up with methods to solve it. So this is a simple optimization algorithms. So we first solve for the rate, then find the power allocation, then find the phase. So just iterate, then hopefully we can find the solution. So we'll skip the details. Let me show you the results. Okay, over here, this is the number of layers in the x-axis, and y-axis is the sum rate. Okay, so you can see, let's say we look at the blue circle lines. Okay, as the number of layers increases, the sum rate get increased. Okay, which is good. But however, after a while, you can see after about 5 or 6, 7 layers, then it gets saturated. Which means that by increasing more number of layers, the performance will not be increased be further. It means that it's saturated. The performance is the best. Okay, and then you compare to the n equal to 149, which means that every layers with 49 atoms versus every layers with 100 of atoms, those with 100 atoms achieve a better sum rate, which means that when this surface is larger, we have a much stronger capability. We can build a better beamforming. Okay, the figures on the right, we are showing the sum rate versus the number of users k. So you can see as k increase from 2, 4, 6, 8, the performance drop, okay? This is fixed, the L is 7 layers, which means that when we have more and more number of users, like increase to 8 or 10, this sim with 7 layers cannot cope with it, okay? The computation power of this sim is limited, okay? I can't build a better G anymore. So the inter-user interference will come in, that's why the performance will drop. So over here, we just fix K is 4, L is 7, which is 4 users with 7 layers. Then you can see when we increase the transmit power, this thing, sum rate, this increase, which means that we are doing correctly. And there is the convergence, how fast our algorithm will converge. Okay, so this is our first work in the SIM. In fact, we presented in the ICC last year that we won the Best Paper Award. And in fact, this is the first job that we did to show that, by stacking these multi-layers, we can build a beamforming. Okay, we can replace the baseband. We can use these multi-layers of the wrist or the metasurface to compute a beamforming G, to carry out the beamforming. Okay, so this is the first thing we did. So after that, we go into the MIMO, which means that, hey, since I can do it for multi-user MIMO, can I do it for the MIMO? And the answer is yes. Okay, so over here, these two diagrams represent the comparison between the traditional MIMO and the MIMO using the SIM. So you can see at the top with this baseband processing, where I need to do my transmit beamforming, then go through the DAC, RF chain, send out the signals. Then after go through the channel, I receive. Then at the baseband, I do the receive beamforming. Okay, with the SIM, I will removing the baseband beamforming. Okay, so all the beamforming will be done in the SIM. Okay, likewise at the receiver, I remove the receive baseband, so all the receive beamforming will be done in the SIM. Okay, later on you can see there are some advantages by doing so. First of all, because the beamforming is not done in the baseband, I need not to have a high resolution DAC and ADC. okay? Because I no need to have a good resolution, a large number of decimal points for me to do the addition and multiplication, okay? Everything is done in the analog domain here, okay? Second, I can reduce the PAPR, okay? Here, the beamforming is done after the RF chain, okay? So the PAPR increase is in the analog domain, but not in the digital domain. So the PIPR requirements over here at the antenna will be quite low. Okay, with this in mind, let's see how we solve this problem. In fact, the formulation is same as the multi-user MIMO, okay? In the sense that, we can formulate the same thing as before, which is on both sides there are how many layers, L layers, the other side there are K layers, okay? So P is the transmit beamforming, whereas Q is the receive beamforming, okay? So for each of them is the same format as you see before, which is the phase multiplied by the channel, W, then phase, W, phase, and W, okay? Which means that by changing the phase at the transmit and receive, I can make any P and Q that I want, okay? So in this problem, G is the channel between the two SIM. And the problems we can formulate as we want to do the SVD, okay? If P and Q, they are exactly the singular value decomposition of the G, okay? After multiply by the P and Q with the G, I will get a diagonal matrix, and every element on this diagonal matrix is the singular value, okay? So I would like to highlight is that over here, what we later on we learn is that using this SIM, basically right now we are solving a mathematics problem. We are doing the SVD, singular value decomposition. We're using this hardware device, multiple layers of metasurface, to solve a mathematics problem in the radio wave domain. Okay, this is how we see it. So with this problem formulated, the next is just how we find a solution to solve these optimization problems. So in this paper that we publish, we come up with a method which I'll skip in details. So the thing is solvable, it's not that difficult, it can be done. Let me show you the results. Okay, in terms of the performance metrics, we're using these two numbers. Okay, the first is the NMSE, which means that after we diagonalize, how far away from the diagonal matrix, okay? So we want the off diagonal to be 0, the diagonal to be as close to the singular value as much as possible. So we want this triangle value to be small. Next, another metric is the sum rate, okay? After we do the beamforming, what is the sum rate of this MIMO channel? Okay, over here you can see, this is the number of layers, how many layers is needed, okay? So this is for L, the K is different lines. So K and L represent the transmit and receive. Let's assume they are the same, okay? So over here, this is the triangle value. So you can see about 4, let's say transmit with 4 layers, receive with 4 layers. You can see this triangle value close to 0, which means that with just 4 layers at the transmit side, 4 layers at the receive side, I can successfully diagonalize this MIMO channel, okay? Of course, this is the case with each layer, there are 100 number of atoms. Okay. Next, if we look at the sum rate, the channel capacity, same thing, about 4 layers on both sides, or 4 to 5. Again, we reach the optimal value. Okay, which means that we successfully diagonalize the MIMO channel and we get the best channel capacity. In this figure is the number of data stream. Okay, which means that we are sending 4 data stream, 6 data stream, or 8 data stream. Okay, this is the triangle value. We want to be as small as possible. And over here, we are fixing both sides with 7 layers, okay? And then we're changing the number of atoms. So you can see the best is 100 of atoms. So you can see this one stay nearly 0 until 4 data stream. After that, then these start to pick up, the errors start to appear. But if I reduce the size of my layers, which means that only 16 atoms on each layer, you can see the performance is quite poor. Which means that this SIM has limited capability. I can't compute so much, okay? But when I increase more and more number of atoms, then my capability get stronger. Means that your processor get better, okay? I can solve the problems and I can diagonalize it. This is what we want to show. Okay, so this one we visualize after we do the beamforming, how the diagonal value looks like. So you can see about 4 layers, the off diagonals are close to 0 already. Okay, so which means that we can do the SVD successfully. So for this work, basically we show that we can extend it to the MIMO. The problems get more complicated because I need to optimize both the transmitter and receiver. both sides I need to optimize them. So the problem is more complicated, but it's still doable. And we show that we can solve a mathematics problem like the SVD. Okay, then the next is that we are going to show you about a problem for sensing, which is finding the DOA, direction of arrival. For this problem is slightly different from the previous two in the sense that over here, you can see this sim, there are two different layers, okay? The layer 0 is the blue color one, okay? This blue color one is the one that will changing the phase, okay? We need to keep updating the phase. Later I can tell you why. And then the rest of the layers, these are the green layers here. This can be passive in the sense that no need to be reconfigurable because these green layers here is fixed to solve a problem of the DFT, discrete Fourier transform, okay? So what we want is that when the signals come in, we do the 2D DFT, two-dimensional discrete Fourier transform. And then we hope that based on the direction where you come from, we focus the energy in one of the direction, in one of the antenna here. So over here you can see we put in the 4x4 antenna array, okay, which means that we can identify 16 directions, okay. If your signal coming from the upper right-hand corner, we will focus energy here, okay. If the signal coming from the middle, we will focus energy somewhere in the middle here, okay. So by a simple energy detector, we can know where this energy coming from, okay. However, if we just use the 4x4 antenna array, my resolution will be very poor. I can only identify one of these 16 directions, okay. For me to improve my resolution, what I will do is that we add in this layer 0, okay. This layer 0 is doing the phase shift, so I will keep shifting this 16 grid, okay, so that I can, by accumulating all by over the time, I can improve my resolution. Okay, so same thing here. This problem, we can formulate the problem in the same way as before. This G again is the W and phase and W and phase. Okay, exactly the same way. Okay, and this is the receive signal model. So, which is modeled as the signals which direction is coming from, then plus the noise. And over here, like I said earlier on, my sim, the green color layers, right, is fixed to match it to a 2D DFT, discrete Fourier transform, okay, which is this matrix F here. So this thing we can solve it offline. Once solved, these green layers no need to change anymore, okay. Unlike the MIMO and the multi-user MIMO, my sim need to adapt based on the channel. Whereas for this case, no need, because it's forever doing the DFT. Okay, with this in mind, then this is the layer 0. So I will keep changing the grid size. So at first it's the horizontal grid, red, green, blue, for example. Then I change the vertical grid, okay? So that I can improve my resolution, not just the 16 grid. Okay, so with this in mind, you can see, the red cross is the ground truth, and the heat map is where the energy are concentrated. So you can see, by the simulation, we can get quite a good estimation on where the direction of arrival coming from. Okay, so let me share a bit more time to share with you, based on what we learned here, what are the problems or how we see this sim and what are the research opportunity. Okay, first of all, you may say, hey, for what we showed just now, we assume the phase are continuous. Okay, so the performance is good. But you may ask, in real life, the phase of every atom may not be continuous. It can be discrete. How will be the performance? So over here, we have done a simulation. On the left is the case of continuous phase shift, means that every atom, the phase is continuous. This is layer 1, layer 3, 5, 7, 9, and 11. Whereas on the right-hand side is the discrete phase, means that every atom is one bit of control, either 0 or the pi. So, and we try to create an image of 2. So you can see, with single layers, the performance is quite bad, okay? But with 3 layers, 5 layers, you can roughly see the share of 2, okay? For the case of discrete, 2 and 3 and 5, roughly you can see something, but it's quite noisy. But still you can see it's doable, okay? In other words, even for the case of discrete phase shift, this thing still works. This is what we want to show. Okay, so in is in short, what we summarize is this. This SIM, right, is a wave-based computing, okay? This thing compute the things in the radio wave domain. Just use the radio wave. We compute the beamforming, everything in the speed of light, okay? Unlike in the past, we do in the baseband, we use the FPGA. We need to addition and multiplication for all the signals that we're sending out. Now, no need. When the signal come in, pass through layer 1, 2, 3, 4, 5, the wave will be shaped accordingly. Okay, this is how we see it. So it's fast, we can do everything in parallel, we can reduce the complexity. Then second, we can simplify the hardware requirements. Like I said early on, we can use a low resolution or ADC or DAC, and also the PAPR. The PAPR requirement will be reduced significantly. And this thing is important in the sense that this is how we see the SIM, okay? First of all, as I mentioned early on, it is a wave-based computing. We can use it to compute something in the radio wave domain, okay, which is fast, which is in the speed of light. Second is that this thing is based on the metamaterial, okay, in the sense that it is reconfigurable, okay, it's software defined. Means right now you can program this thing based on your channel. When your channel change, you can reprogram it to fit your channel to compute a new beamforming. Or today you can use it for the multi-user MIMO, next day you can use it for MIMO, next day you can use it for DOA, okay? This thing you can reprogram it for multi-purpose, just like your FPGA, just that it's in another domain. Then the last thing is important is that how we see this thing is that you can treat these multi-layers like a neural network, okay? So, but it's a neural network in the radio wave domain, not the electrical signal, okay? So what it means is that anything we can solve with neural network, like classification, etc., as long as we can model the problem accordingly, we can solve it using the SIM, okay? But of course, in the neural network, there are things like LSTM with the memory, with feedback. This is something that we don't know how to do it yet using the radio wave. But if just feed forward way, this can be done. Okay, so this work in recent years, there have been quite a number of papers being published. You know, people have been using it for physical layer security, using it for cell-free, so on and so forth. Okay, these are not the exhaustive list because more and more papers are coming out. But we have seen that people have used it for various problems in the wireless comms. And over here, like the example I show you, we have used it for the SVD, do it for the DFT. You know, we use it to solve some mathematics problem. Okay. Then for this slide is showing some of the so-called prototype, which we convince ourselves that, you know, this thing is possible. This is done by the Southeast University, okay? It's the one closer to us, okay? They have this horn antenna as the excitation to send out a radio wave to excite the whole things. Then they'll put the image here, okay? What they do here is to do the image classification. So if your image is class 1, they'll focus energy in one of the corner. Class 2, another corner. Class 3, another corner, just like the DOA. Okay? So over here is the FPGA, where they program the phase and also they are amplifiers. So when they pass through every layer, they amplify the signals. Okay? The one on the far right is done by NUS, Professor Zhining Chen. So even though it's very thin, right, you can inside is three layers. It's a 3 layers of meta surface. Okay, but for that one is the static, means that you cannot reprogram. Okay, but what they do is that when the feeding horn, like the antenna send out a beam, after passing through 3 layers, the beam becomes very sharp. Okay, basically it's doing the beam forming. Just that the beam direction is fixed already because this thing cannot be reconfigured. Okay, this is just published a few months ago by Tsinghua. So they are doing it for DOA. Okay, it's same as what we do in DOA, but they have made a big prototype. And this one is what Marco has reported just now. He's partnered with China. They've done a 2 layers single bit SIM. Okay, so over here, what we convinced is that this thing is possible. It is doable. Okay, and it shows a lot of promising application. And what we understand now is still limited. Okay, the next, I'm going to share with you another 3D structure, okay, which we call the flexible intelligent metasurface. Okay, so for those who are doing the material science, etc., okay, over here you can see they have done various flexible metasurface, okay. This thing, the shape it's flexible. You can bend them. You can change the shape based on various methods. Okay. Then next, I'm going to show you a video by Duke University. So over here, you can see they can control this surface in the sense that you can make it to become different shape if you want.
Basically, the current existing morphing materials are mostly programmed. It's like origami, right? You set those creases, and so the surface can actually fold into a certain shape. So right now we are trying to see, okay, whether we can control the entire shape morphing processes instead of like just controlling this like initial shape and final shape. And so this is like why we want to be able to program the shape in a real-time fashion. And so this is actually not a very easy idea for soft surfaces, because imagine that if you have like a soft blanket and you have some object underneath, but if you take that object out and if you want to still maintain the shape of the blanket in the same way, and how are you going to apply the forces, or how are you going to deform them to maintain that shape? It's actually a very difficult problem. We call it inverse problem. So how to find the control signals to actually get the output shape that we want is the key idea of this project.
Okay, so we ask ourselves, since material people, they can build such device, material, how does it impact our communications? So that's why we look into this thing, which we call them the flexible intelligent meta surface. So again, we consider a communication problem. Again, we use the multi-user MIMO as an example. Okay, so over here, we assume the N is the number of elements. Okay, we just treat every element, this N, as the antenna. Okay, of course, you can treat them as a reflector. Everything is okay. Okay, over here, we just treat them as an antenna element on this surface, the atom. Then K is the number of users, and L is the scattering. How rich is this channel? The number of scattering is inside this environment from the antenna to the end users. And over here, we assume every element of the antenna, right, on this meta surface, they can move within a range. Okay, so we assume then you can move between Y minimum to Y maximum. This is what we call the morphing range. You can move between this range. So this surface will have this shape formed by every element. Okay, so right now we just assume that the movement is along the y-axis. Okay, so you can see the y-axis is the vertical, the axis that's perpendicular to the surface. So with this in mind, then we can formulate the problem. So the A is from the scattering to from the FIM to the scattering. Then the channel per user, we can write them as the H. So H is in terms of Y. Based on the movement, the morphing of every element, the channel will change. Okay. And with this in mind, then we can write down the SNNR. So same thing here. The problem is how we can maximize the SNNR by finding the Y value. Okay. Of course, we can add in power location, etc. Okay. So we skip the details. We solve it for the single user, then solve it for multi-user. Okay. So let me show you the results. Okay. So in these results, right, you can see they are top and bottom. For the top, corresponding to the morphing range is half lambda, which means that the range we can move is half lambda. Whereas at the bottom, the moving range is lambda, means that the movement is larger. I can move by lambda. For the left and right, for the left corresponding to L equal to 4, means that the environment, there are 4 scattering. On the right, L equal to 8, means that there are 8 scattering. Okay, the environment is more rich. Okay, let's first compare to the left and right. You can see at the top, both are half lambda. For 4 versus 8, right, 4 versus 8, you can see the gain of the 8 is larger, which means that when the environment is rich, by moving the element, I can get a higher gain. Okay, simply because there are more scattering, the diversity is there. So when I move, high chance that I can find a position that with a better the reflection path. So the red color line, right, is the gain. Okay, by moving, the case of the moving versus not for non-moving. Okay, so the gain we show here is the maximum gain per element. What is the maximum gain? If you're comparing top and bottom, right, you can see with the moving range is larger. So by common sense, we know that the gain will be larger because I have more degree of freedom of movement. then I can get a larger gain. So this is the work we've done. Then if you comparing the case of the rigid array compared to the FIM, the one that we can move, so you can see by having the same SNR, I just need less transmit power. Okay, I just need less transmit power, I can achieve the same SNR. Okay, so for this result, we're showing you the morphing range. Okay, so we from 0 to 0.5 lambda, 1 lambda and more. After a while, you'll see that it will get saturated, which means that even you can move more, but it does not help. Okay, so somewhere around range here, from half lambda to 1 lambda is good enough to get the best gain. So this is what we find so far. And over there is in terms of the number of users. Okay, so in short, for these two parts, right, what we show you is that we are showing a 3D. You know, in the past, we will go from MIMO to single antenna to MIMO to relay to massive MIMO RIS. We are seeing the antenna from a single element to a linear array, then to a 2D surface for the wrist. Okay, so that's why it's quite natural is from the 2D become for 3D. Okay, and then for 3D over here we show you two structures. One is the multi-layers structure, which is the SIM. Then the other one is a 2D structure, but this thing can move up and down. Okay, then it's the FIM. Okay, and what we believe is that what we understand now is still limited. There are a lot of things we still don't quite fully understand, and there are a lot of problems, you know, like what is the loss, etc., that we don't fully understand yet. But I believe this topic is exciting, and hopefully in the next 2 to 3 years, we can solve most of the problems. Thank you.
Thank you so much, Professor. Is there any question in the room? Yeah, please. Then we move to the second. Yeah, any one of them. First, yeah.
Hello. So for the prototypes, you've shown us 2. And for the second, you've mentioned that for the SIM, it was not reconfigurable. I wanted to ask if that's the case for SIM in general, and if so, because if not, then I wanted to ask what prevents the reconfiguration, and if it is the case, then do you still believe that even without reconfiguration, it will outperform RIS in all cases?
Okay, so in fact, this thing is same as the RIS. When the RIS first come out, you know, people has the so-called passive RIS, means that every pattern is printed. Okay, then later on you can see we have the prototype of the RIS where I can configure the elements to change the phase. Okay, same thing here for the 3 layers. The antenna person, when they design the thing, they design the pattern, they fix it. Okay, so they have not go into the stage that adding in the elements to control it yet. Okay, but from what we know now from the discussion is this: the loss of the NUS, the antenna, the loss is very small. They can pass through 3 layers, is like less than 1 dB of the loss, much less. Okay, but what we know is that once we add in the control element, those elements will introduce additional loss. Okay, so when you have even 1 layer, you can pass through like 0.9. 3 layers is 0.9 to the power of 3. So the loss will increase. So this is one critical problem that we need to address. Okay, and then for when we, and then just now, if you remember, I mentioned also a strong assumption is the equation 1. Okay, we assume that the channel is by the near field, the equation. But once you add in the control element, how the channel will looks like is not predictable, or at least we don't know yet. Okay, so this is something that unknown that we need to address.
Thank you.
On this topic, it's very interesting. I just have one question, which is about the channel estimation. I don't think it's going to be very easy to estimate these large dimensional channels with the limited number of observations you have at the base station, because the number of antennas is, I'm guessing, way smaller than the number of meta-atoms you have at the last layer. right? So
Yes.
do you have some works around that? How do you see that working out? And my second question, sorry, one more question. So the sim, the prototype, did you measure the losses with the number of layers? Like, did you see any losses, the amount of loss increasing with the number of layers you were introducing in terms of the amplitude or the signal gain? Thank you.
Okay, so for the first question, yes, this is one big problem because if you look at the MIMO, let's say I have 4 IF chain, the IF chain is just 4, the dimension is 4. But when I expand it to the sim, it's 100 by hundreds, if the atoms is 100. So the dimension is much larger. So we need to use some kind of compressed sensing techniques to do the channel estimation. So in fact, we have one paper published which we talk about the channel estimation. But I agree with you that there are a lot more problems that how we can address the channel estimation, like using some codebook-based method or whatever the method, which is still is unknown. Okay. Then second, about the loss, the prototype, you can check with macro about the 2 layers things, but I don't think much people has measured about the loss for the reconfigurable sim yet. So again, these things still unknown.
Okay, thank you so much, Professor. Let's give applause and we start with the coffee break. Thank you so much. Let's back after 15 minutes. Thank you for your patience and your attention.
Okay, good afternoon, everyone. It's very nice to be here. My name is Annie Nadeem. I'm an assistant professor of electrical engineering at New York University, Abu Dhabi. And I have to start by saying that what a wonderful summit we've been having these last 2 days. And what a wonderful set of topics and talks we have heard over, these last 2 days on such a diverse range of topics, from meta-surfaces, to integrated sensing, communication, and localization, to integrated AI and communication, to digital twin, to, metaverse, and so many interesting topics have been covered, and so many interesting use cases and applications have been brought up in all those different talks, which kinds of shows, what is driving this evolution towards 6G. And also makes one think that 6G is not just about new enabling technologies and additional spectrum like 5G was. It's more about, or I would say it's also about the new use cases and applications that the networks now have to support. And also the new functionalities like sensing, localization, computing, all of this with connected intelligence that the network has to support. So, this is what motivates this panel discussion on multifunctional 6G networks, key technological trends, and challenges. The discussion will be centered around, how the 6G vision is shaping up in terms of integrating these different functionalities, sensing, localization, computing, AI, with the conventional communication framework. What are the main use cases of, these unified platforms? And what are the main technological trends that would facilitate or enable this integration? And also the challenges on the road to, successful integration of these functionalities and tools, under the same wireless resources, the same spectrum, hardware, waveform resources that our conventional communication systems kind of use. So I have with me 4 experts from academia and industry who will be sharing their thoughts on different aspects related to this topic. I'll start by briefly introducing each of them. To my immediate left is Professor Nawaf Al-Musa, who is the director of the Emirates ICT Innovation Center and an assistant professor at Khalifa University here in Abu Dhabi. Professor Nawaf's research interests include optimization and control with applications to computing and telecommunications. Thank you, Nawaf, for joining us today. We look forward to hearing your perspective. Next, we have Professor Marco Di Renzo. Marco is a professor at Central Sapelec, and he is very well known, of course, for his contributions towards different multi-antenna communication systems over the years, for his seminal works on reconfigurable intelligent surfaces, and more recently for his work into the application of these meta-surfaces as transmitting and receiving surfaces. Marco is, of course, the recipient of several Best Paper Awards, which I'm not going to list because it will take forever, Marco. So, but, it's really nice to have Marco here. Marco, it's very nice to have you here again and, to hear your perspective. Our third panelist, I'm very excited to have her here, is Ms. Najla Al-Khabi. She is the head of artificial intelligence at Do, which is a telecom company in the UAE. And Najla has been very active. She has been at the forefront of this strategic evolution towards AI integration, not just in Do, but I would say even nationally in the UAE as well. So Najla, we are very, very excited to have you here and hear your perspective as to how, AI integrates into the upcoming generation that we are now talking about in this summit. Thank you for joining us today. And finally, we have Professor Henk Weimert, who is a professor of communication systems at Chalmers University of Technology in Sweden. Professor Henk has been working at the intersection of communication, sensing, and localization for many years now and has made fundamental contributions in this area. He delivered a very interesting talk yesterday, which I had the privilege to attend. So thank you very much for that as well, and it's really nice to have you on the panel. Okay, so I'm going to get the conversation rolling, but for me, the success of this panel depends on the ratio of the questions you guys ask to the number of questions I ask. So, I'll be coming to you very shortly to take any questions you might have on the different aspects that are discussed here. But just to get the conversation started, I will, start with some of my own questions, which, as you might have known by now, are quite a lot. I do ask a lot of questions, so let's get started with the first question. We're talking about multifunctional 6G networks. So this question is open to all 4 panelists here, and I would like to hear everybody's perspective very briefly. Which functionalities do you think, in terms of sensing, in terms of localization, in terms of computing, in terms of, all of this under the umbrella of connected intelligence? So which functionalities do you think are really relevant in 6G? And when this question, I would actually also like to hear, if anybody can share, in terms of, what the service providers are looking for, which functionalities are they really interested in? We have a lot of research going around all these ISAC systems, integrated, communication and computing platforms. But really, in 4 or 5 years from now, what are we actually going to see happen in terms of their integration into the existing communication frameworks? So the question is open. Whoever wants to take the lead is welcome.
Thank you, Professor Qurat Al-Ain, and thank you very much for our esteemed audience for staying with us. Hopefully, we'll entertain you. I know we'll try to be both informative, but also maybe provocative whenever the chance allows. I don't know. I think just with 6G, remember the a famous author said, "There's no new book. Every book is a superposition of old books," and that has. It felt like that. I think in one of the keynotes here today, if that allows you to, to me personally, and also from what we hear about how operators are struggling with cost, if you can replace, it can be a modality that reduces the cost. Both of CAPEX, but also the cost of the computing needed for signal processing, beamforming, etc. So there you go. I pitched in. All yours. Yeah. Marco, what do you think? Sensing, localization, computing. What's going to come up?
Yeah. So I guess that's. It's never an easy question. To say what is going to happen. In the next few years. But I think that communication, sensing, and localization for sure. Will play an important role. So now, as far as I understand, the next year. Around the third quarter, more or less, there will be these discussions about the 6G, and definitely, integrated sensing and communications will play a fundamental role there. So now I'm not a standardization person, so I'm not directly involved in this kind of discussions and activity, except a bit that maybe I will tell later on. But definitely, this will play an important role. So now, regarding computing, I really would like to see computing as part of the discussion. So I heard a lot about this in-sensor computing. So I think when it comes to energy savings, to reduction of complexity, I think the possibility of not having sensors and then having analog to digital conversions and then all the processing, but having a whole of this, embedded together, it may bring on the same device. It may bring some advantages in terms of complexity, power consumption, etc. So considering that in any case energy efficiency will be an important aspect, I think that these two things together, I really would like to see them. Then, when it comes to the technology to make this possible, of course, you were mentioning about these programmable surfaces. So if we want to really see this multifunctionality or multifunction, I think we should have the platforms that allows us to do that. Yeah, that's definitely, for sure. So I think that many things that were discussed, in the past, were not, they didn't materialize them because maybe we did not really have the technology to do that. Now, there was this excitement about this reconfigurable devices, reconfigurable materials we saw in a few presentations, So I think that if we will be able to make them really reconfigurable and really cheap and low power, which for the moment is not clear whether they will be cheap and low power, I think that maybe they could be a platform. But they could be a platform to integrate communications, localization, and sensing. So I think that these three things, will go together, and I would like to see them integrated, in the device, rather than having all these blocks, together that just take space, takes cost, and consume a lot of power, a lot of energy. But it's difficult to predict. Sometimes, the best scientific and technical solution is not necessarily the one that you will see in the standard. So I think that there are other factors that comes into play. But let's see. Yeah, let's see. Yeah.
Yeah, no, and personally, you think computing is an important functionality that, should probably get more attention, in my opinion, as well.
Yeah, let's see.
Yeah, but that's our opinion, right? Najla, so I would also like to hear, in context of this question, Do's perspective generally, as much as you can share that, which services or which, kind of functionalities are they actually looking at, in terms of integrating into the infrastructure that they already have?
Well, I come from a service provider, and what drives us is what the customer wants.
Of course.
So the story always starts with what application we need to empower. So all these functionalities are important for us as long as there's a demand, as long as there's application. We have seen that how 5G was promising a lot, but nothing has been achieved except maybe for the broadband bandwidth. The ultra low latency is still not there. The massive M2M is still not there. But the application that the customer want, either that was autonomous driving or what they call it, the haptical sensing, I forgot this one, the holographic, all of these, the remote surgery. We as a service provider, and this is our bread and butter, we have to evolve. The technology or the approach that we have taken since 2019, I would say, when we have seen this, this demand for enhancing our network to accommodate more and more functionality over time, is the ability to manage it without increasing our OpEx, without increasing the operation. So we started with automation. I would emphasize the importance of AI to deliver what 6G is promising, and to be aligned with our approach. We want to keep our OpEx down. We want to make our network autonomous. We want to do a lot of what 6G is promising, but we cannot do it with human resources or adding more humans in operating the network. We need AI. So basically it's AI.
Yeah, yeah. And the theme of this summit has largely been AI and communication, so rightly so.
Yeah, and honestly, I'm not a network engineer, and IT and AI, so you will see me more in that direction.
Yeah, yeah. Henk, what's your perspective on this?
Yeah, so I tend to agree with my colleague that it's a lot about what the customer wants and also where the operators can make money. And if we think about, for instance, what happened in 5G, there was a lot of promise with millimeter wave, but it never materialized, right? And I think we may have very good technical solutions for problems, but if nobody's willing to pay for them, they will never be deployed. And I see this risk emerging again with sensing, right? So many people are worried about being sensed. Maybe it depends on which country, but there's definitely this risk. And then again, for sensing and also for positioning, people are used to getting some services for free. I have GPS on my phone for free. Am I willing to pay a few dollars extra just to have a little bit better positioning? So there's challenges there.
So, when we talk about these integrated functionalities, I think it's very use case specific. I'm not sure if sensing or localization is something that will become an integral component of, your 6G core. It largely seems to be very use case dependent. For example, Isaac for transportation, Isaac for healthcare, where it might have a lot of potential. But, I have read a lot of papers. I'm not an Isaac expert. We do have some experts here in the audience. But, I've read a lot of papers where they talk about Isaac, being very beneficial for the communication system itself in terms of improving the performance of your radio communication system. So, based on that, what kind of use cases do you envision for Isaac? And, all these, you can integrate localization into it, AI. And AI, I feel like, might have a lot of use case from end to end, but generally in terms of sensing and localization, what do you guys think, in terms of use cases? Are they very specific? And if they do add a lot of value to the communication system, then, does it really make sense? I know at the end it depends on service providers and operators. I mean, we can't say that, especially from academia. But what do you think, are the real use cases?
Yeah, so I mean, in Sweden we work a lot with local industry, with Ericsson, Nokia, so we talk a lot about this, right? And then obviously at the physical layer there's a somehow tension, there's a trade-off between sensing and communication. Whatever radio resources I devote to sensing, I take away something for communication. The only way that you will have a benefit is at higher layers, that the sensing information can be used for communication.
Yeah.
And then, of course, there's very high layer aspect related to analytics, but maybe also lower layers. But this can only be really harvested when there's some geometric information in the channel. So this is really meaningful at higher frequencies, millimeter wave and above.
Yeah.
At lower bands, it's really unclear if this sensing information can add a lot of value, except maybe some applications like channel charting and such.
Yeah, yeah. Okay.
I mean, certainly, you know, if I know of any good use cases, I wouldn't tell anybody.
Okay.
Yeah, that's the not billions dollar question, probably. But also about your earlier question about and the parallels with I mean, if I may call it disappointment with 5G. I remember earlier, like in the early in the rollout for 5G, there was an article, I think it's in The Economist, that is 5G the new 3G? I mean, you can draw parallels because you know, it was also disappointing, but it kind of was a prerequisite or set the stage for 4G, which was, I guess, mildly more successful.
For sure.
So the question now is 6G the new 4G?
Yeah.
That's yet to be determined.
Yeah. I'm going to ask a question that is a bit off topic because we've been talking, this point has been brought up a couple of times about 5G success. What's the hurry then to get to 6G if 5G has not realized its full potential? Have new use cases emerged? Again, without revealing them, but you know, what really is pushing us towards 6G then, if you know 5G? And I agree with that. I've seen this discussion happen at multiple other platforms as well. So you know, what is driving the service providers and you know, even academia towards 6G research and development? Nobody's willing to take that question.
I'm still dreaming about network slicing.
Yeah. Okay, so in terms of, you know, when we evolve towards 6G, there are different technological trends. Let's talk about technological trends then. You know, 5G brought up massive MIMO. Massive MIMO, I think, has largely been, you know, one of the more successful technologies. Network densification, irrespective of the cost factor, has potential and has been implemented, you know, with these small cells, indoor hotspots, and all of that. So in the context of 6G, different technological, you know, advancements have come up. RIS is one of them, as Nawaf pointed out, and Marco, of course, has been championing, you know, that aspect for quite a lot of years. Then there have been discussion about holographic MIMO. There's also a lot of discussion around non-terrestrial networks, terahertz, FSO. So, you know, what kind of technologies do you think, you know, are really needed in terms of, you know, especially when we talk about integrating these multiple functionalities into the next generation? Which technologies do you think have a lot of potential? RIS, of course, like, you know, you pointed out in terms of sensing, and also computing with all these talks about the metamaterials, the SIM, have a lot of potential. But generally, you know, which technologies, you know, if we draw parallels with 5G, do you see are becoming, you know, the talk of the town? Whether they are successful or not is another story that we'll find out in a couple of years.
So I would like to comment. So again, I talk a lot with companies, right? So maybe it's not very academic perspective, but probably not RIS, probably not NTN,
okay.
Definitely not terahertz, probably not FSO, definitely AI.
For sure.
AI will have a transformative impact, right? So I think AI is really the thing that will change everything. How exactly, I don't know.
I can add a little on this. So when we started our automation, you know, eventually what we are doing is we want to reach an autonomous network that can self-heal itself, self-manage itself, do beamforming automatically, do slicing automatically, allocate resources automatically. So when AI is becoming more popular or more obvious, especially also with the Gen AI, it made a paradigm shift in our way of thinking how we should automate our network. So instead of considering AI as a hyper automation, we said, okay, it should support us in making decisions.
Yeah.
And that's the beauty of AI, as we all know. It enables the machines to have this capability of learning and self-learning and enhancing its performance. regardless of the challenges that come with that and the risk that comes with that. So what 6G is promising to do is or what customer will push us toward accelerating adapting 6G will depend on how fast we also adapt our AI in our network. And it's not an easy job. It's not an easy job. It's not plug and play. If you look at all the telcos around the world, how they are adopting AI in their network, it's a long journey. Some of us is ahead, some of us is still at the beginning, some of us is still learning, some of us is taking just focus in the operation field, some is going a little bit cross-corporate. And I want to emphasize here, if you want to adopt AI, it's a digital transformation and it's a mindset kind of approach. I can talk technically about how AI can do things, but the greatest challenge is how to convince people and how to make people believe in the power of AI and how to transform their mindset to native AI or AI first. So it's not a technical discussion, in my opinion, more of really adoption discussion, culture, and people change.
Right, yeah.
Yeah, I just think maybe to me one of the, when it comes to the technologies, one of the most, that will be impactful, one of the most exciting things is maybe something boring, which is reducing cost. Mm-hmm. But it's a huge, the total cost of ownership is a huge, there's always a question mark about investing in new infrastructure. If there's, you have to obviously have the revenue from services, etc., but the cost itself. So any technology that will help with that, or AI, for example, if the chance for resource adaptation, to reduce, for example, the OPEX, the energy consumption, etc., that will have huge benefits. But also maybe even innovations in the network architecture. Yes. For example, some of the elements of the open RAN standard, where just the idea that you can have kind of virtualized, disaggregated network, and you can reconfigure. So the nodes could be RUs and DUs and share them. Whether it works well or not, that's a different question. Yeah. But that's something exciting. Yeah.
Marco, what do you think would be like in terms of technology?
I agree basically with what basically was said. So we have been working now for a while on, for example, this RIS, etc. But I don't think that actually will be. It's too early. That's definitely for sure. I'm seeing. In the best case, it's too early. But I've seen. Discussing with some companies, etc. That so they would like to reduce the cost as much as they can. They are trying to repurpose the hardware that they have in order to do other things. So I think this would be, it's not really a technology, but rather, to take the best out of what is already there. That for sure, AI will play an important role. That's I agree. Now, when it comes to the technical robustness of AI, I'm not an expert, so I cannot really comment about that. But this is also something that should be considered. So coming back to the ISAC, and to the sensing functionalities, I think it will play a role. At least, it will be there. I think so. That's that is what people say. As I said, for ISAC, I think there is a 3GPP work item already, so they are working about that, so it's much more advanced. The other technologies like RIS, this does not exist, for example, so it cannot be there. I don't believe there was a lot of interest a few years ago on terahertz, but I don't see it either. I agree with you. So we are going back towards other kind of. So the spectrum would be different. It will not be there. Yeah. Even though it will make a lot of sense because you have a huge bandwidth, and so of course your sensing capabilities will be better. But there is no availability, so the coverage is too small to handle it. Yes.
So
yes,
there's one technology we haven't talked about, which is like self-free MIMO or distributed MIMO.
Yeah.
What's the potential of that, if I may ask a question?
Yeah, for sure. I think that's a very good question because self-free and open RAN and, the C-RAN architectures, I think they are, absolutely amazing in terms of, interference, which has always been considered to be a bottleneck when we talk about, our cellular systems. It has always been the bottleneck. So, self-free combined with, these open interfaces, I think it's a very interesting direction, but I would love to hear everybody's thoughts as well, on this. But good point, excellent point, I would say, yeah, to discuss.
Who was the question for?
You asked the question.
So self-free MIMO, I think it's a great technology, but it has to, the whole idea of self-free, I think from the physical layer, we need, some integration with the higher layers as well in order to make self-free really a success. That's my own thought process coming from a massive MIMO background. But, when we talk about, there's been discussions about AI and, let's say we keep all these functionalities into the picture. What levels of integration are we looking at? Are we looking at, these very high level, kind of integration where, let's say, AI is used for, cell switching, like Nawaf was talking about sustainability, energy efficiency, this cell management? Or are we looking at deeper level of integration, with hardware reuse, with spectrum reuse, with, and this also applies to sensing and all those applications. With, for example, for sensing, there's so much work on waveform design and signal design. Are we looking at signal reuse and waveform reuse, in practice as well? So maybe Najla, I can start with you. Let's say for AI, what levels of integration, are we interested in at the moment?
That's a very good question, but honestly, I don't have the aspiration is very high. We want AI definitely to be everywhere. As we say, the decision making, where there is a point for decision making, and AI can replace it. Let's put AI there. But this is very challenging. If you think of now, currently we're talking about agentic architecture, where you will have multiple models in your IT system, let alone your network. And these models should talk to each other and should make a decision or should, aggregate kind of suggestion or recommendation for a human being or for another supervising agent or orchestrator agent. We are still at that phase of putting the design principle for agentic architecture. Where will the level of integration in making the agent pervasive within your IT information system? The same should be in the network, and you will merge your network architecture with your agent architecture, or you need to put your models in a way that is integrated in the network functionalities. I don't come from network, but I think that will be a huge challenge. Especially that if we are talking about the challenges that come with AI, making decisions or predicting you use neural network, and neural network in its behavior and nature is sometimes people cannot explain why they came up with this decision. It's somehow a black box, and you need explainability. So if you will make a decision and it will be really difficult to explain why you reached that decision, it's either you make the human being might make that decision way much faster than the machine at that time. So it will be, you need to strike a balance between the risk associated with your model and the speed that you will get it out of deploying AI in your network.
Yes, I agree.
So some really serious architecting is happening at the beginning before we go deeper. When it has come to doing model here and there, we've done that across our network in different use cases. For example, the energy efficiency. Yeah. We have done it for this, controlling the sleep of our base stations. We haven't yet done it closed loop. We are still also at that phase of gaining more confidence. We're just giving recommendation for our, and again, imagine that difficulty in one model only. A model that has two competing objective, an objective of you need to maintain the performance KPI for your customers, and you need to also save energy. So two competing objectives, and you have to be very careful in making that model precise in making the decision. And it takes time, and it's the maturity of your model takes time. So think how you can integrate that across all your network.
Yes, yes. So sustainability has been brought up, and I think that's a very important aspect. So, in terms of sustainability, do you think, we need to give more attention to this particular aspect? Because, technologies have come up, and I'm happy in this decade we've been talking about risks and meta surfaces and AI for, energy efficiency as well. But there have been talks about these low-resolution data converters, how they can impact. So, is there work going around in terms of, standardization, in terms of, is this aspect being taken into account? Because, you guys, of course, have way more experience than I have in this particular area. How much attention is sustainability being given when designing these technologies and frameworks for 6G?
So I could make some minor comments here. So I'm part of the Hexa X2 project, which is the 6G flagship. And their sustainability, I think, is about 1/3 of the whole project. So this is a 20 million euro project, and 1/3 is just about sustainability. That's the good news. The bad news is that, for instance, in terms of outputs from this activity, I think there's only one white paper. So there's a lot of discussion ongoing, but little in concrete results.
Yes.
A lot of work is on life cycle analysis, looking at the system end to end. But I think at the same time, there's also low-hanging fruit, right? There's just like reducing OPEX. Base stations are using so much power. Can we just reduce that with a half? Operators will save tons of money.
Yes. Yeah.
Yeah. I mean, I can maybe start also from the previous question that you asked about the integration. So I mean, regarding the integration, I guess the sharing the sites, sharing the hardware. I mean, this is something that definitely, I mean, it would be very, very useful also, I mean, to reduce the cost, to reduce the, I mean, not to have different hardware, so cost, power consumption, etc. I mean, regarding the sharing the waveforms, it's something that we do all the time, I mean, in paper, so we have fun in doing that, in conceiving new waveforms, the best that we can do. At the end of the day, I mean, we know already what the waveforms will be, so I mean, it will be FDM. So, and basically at the end of the day, the job is how to fit the sensing into FDM, so there are some proposals. So I guess that I mean, sharing the waveforms most probably will be done, but it will be maybe longer term. I agree with the fact that we are, I mean, many of us are physical layer people, so one is a matter of sharing is always, the signals, the frame and the physical layer, but it would be very important to make the sensing information fruitful to the upper layers. So, I mean, to create the API, to this kind of integration at the upper layers, I'm not an expert, so I cannot comment, but I feel that it will play an important role for that. So regarding, I mean, sustainability, I mean, I don't know. I see that the vast majority of what there is around, I mean, I agree with you, there are these big projects, and then, I mean, maybe the output is not exactly our expectations about that. But I mean, many of the research works on sustainability, at the end of the day, they turn out to be energy efficiency optimization or power minimization or something like that. But right now, I mean, I've seen some new activities, new projects, especially because of these new materials that are being proposed, where people, especially people working on the materials, on the device, on the antennas, that they start wondering really to sustainability of the materials. So try to start building materials that are sustainable, so to build new devices that are sustainable by definition. I'm not sure how much we signal processing people or communication people can do on that, but I think that is promising the fact that people working on antenna design, metamaterials, they are looking into that. Also, I mean, I was doing this example before about reusing the hardware, etc. If you reduce the hardware, you could also, I mean, trying to be a little bit more sustainable rather than also building something new. But I agree that it's still, I mean, maybe to be provocative, but it's still a buzzword. So the sustainability rather than something really concrete. I mean, at the moment, at least, I mean, in our field, in what basically we are doing.
I mean, if it's again tying it to the OPEX part, I mean, if we select maybe one aspect of sustainability, which is reducing related to energy consumption, I mean, it's not only, I mean, the other you can look at it as sustainability, but also as the viability of the business model itself. So, yeah.
It's like a
exactly.
trade-off, yeah.
So there is, I think, there's a common interest, you know, towards that goal, because the figures, I mean, the figures that was just seen before you know, before the panel started. I mean, it looks, the cost of OPEX is really huge, even relative to you know, the CAPEX cost. So sure, there's I mean, the first question is, okay, who's going to pay for it? Is it going to pay for itself? I mean, is it going to pay itself? It's fine, but I mean, reducing the total cost of ownership and the you know, it means energy-hungry devices, so it changes the technology, but also whatever, you know, kind of system you have, if it's efficient and managed properly, I think it's one of the you know, the key goals going forward.
Yes, yes.
I think that brings us to a very good point, in a sense. We are going to face this issue of, especially with the GPUs and this, you know, high utilization for energy. Our interaction with our partners and vendors should differ. I think our business models with them should enforce more of requirements for energy efficiency in their hardwares, in their services, and make them accountable. Make them accountable. 6G is also is going to be energy hungry, and those big players, no need to name anybody, those big players should be the ones who should provide me with a hardware that's already efficient and already built in features. I don't have to take care of that as a service provider.
You know, Najla, that's a very good point, because I think the change really needs to happen, you know, from, you know, really the way, you know, this equipment is manufactured, these RF chains, you know, you can work with lower resolution data converters, you can go, you know, with, you're working with Massive MIMO, exploit that. Massive MIMO was, you know, one of the motivations was that, you know, you can get around, you know, these hardware limitations with a larger number of antennas, but we are still using like 14-bit data converters in our RF chains. Why are we doing that? So, you know, the change really, it's not, the onus is not just on the service providers to, you know, kind of reduce this energy consumption and carbon footprint. This needs to happen, you know, starting from the vendors who are making the equipment. They need to think about it as well.
I have two comments. I mean, to come to your point about these ADCs and etc. I mean, the hardware per se. So there are these papers and scaling law on the scaling laws on the gains that you can have if you reduce the number of, I mean, if you reduce the number of bits. So the gains are claimed to be exponential with the number of bits. Then, I mean, whether this is going to be true in practice, nobody really knows. There are many colleagues who are more in the hardware design, hardware accelerators, etc., that are very skeptical about that. Of course, I mean, reducing all this will contribute, but what the real gains will be is not really clear, except for this scaling law that for the experts seems to be too optimistic. Then, I mean, I have maybe one question, because I mean, I'm not an expert in AI, no, but so I mean, we are all more or less familiar about the amount of power that the AI consumes for training, but maybe sometimes we underestimate the amount of power that it takes for the inference, because even though, I mean, one single inference may not take a lot of power, but we ask queries quite often.
That's true.
And there are many people who do that. So what is happening around that? I mean, so.
Well, I'll tell you what we've learned so far from, we are seeing the trend of LLMs going smaller. So this is a good thing. In the agentic architecture, and we are building these use cases that some of them will be internally and some of them will be externally. And for any query that we have received, we should build different guardrails before I hit the LLMs. One of them for example, if it is a customer-facing query, some of them just to have that, you know, sanitizing for the words before you hit the LLMs, or is it, you know, should I pass this query or not based on what it entails? That's something. But another thing is also, for reducing the need to hit your LLM and hence do an inference. So I can see a lot of, you need to cache some of these prompts or some of these answers, no need to go there. That's what I have seen so far. And I have seen the infrastructure also, people with the GPUs and do we have good partnership now with, of course, NVIDIA and also Sambanova. And we are in close relationship to understand what technology they are having so that I don't need to hit or I need to consume that GPUs or RDU and consume that energy.
So maybe
it's
I
a learning
can just
curve.
see if the audience has any questions at this point before we wrap up this panel. Yes, we have a question there.
If it's anything network for the gentlemen here.
Sure.
AI, I'm happy to answer.
Sure. Hi, this is Adnan from Enritsu. So I have a comment and a question. The comment is, I think what the gentleman talked about, the fact that 5G is a new 3G completely makes sense, because what I believe in is the unsaid law of success of even Gs. So 2G, 4G, 6G, hopefully we're going to make some money over there. But coming back to my question is regarding integration, communication, and sensing, or JCAS, right? Playing the devil's advocate, I would really like to understand, there are other sensing technologies. You have radar sensing, has been there forever. You have 802.11.BF in Wi-Fi that can be used for sensing. So if we look at basically using network as a sensing, even 3GPP has about 32 use cases. But what exactly do you think we can make money? Because that's going to require us to upgrade your base stations to support full duplex, for instance, to really get the functioning out of sensing. So is there a real use case or a real problem that we cannot really solve with 802.11BF or with radar sensing, that we need to use communication channel? As what the gentleman said, that yes, even if you use reference signals, we are using resources from communication for sensing. Thank you.
Thank you.
Okay. So sensing is not just monostatic sensing, right? There's other sensing modalities. There's bistatic sensing, multistatic sensing. And I agree. If you want to have monostatic sensing, you need to have a full duplex transceiver, which is probably much more sensitive than a full duplex transceiver for communication. So maybe that's not worth it. But you can do bistatic sensing, you could do multistatic sensing, and in particular, bistatic sensing would be very much related to communication, right? So there's a bistatic sensing between a base station and users, or users and base stations, and this would provide potentially valuable sensing information for external applications, but definitely for the network itself to optimize its operation. As I mentioned before, I think this will be the first use case of ISAC, just to improve network operation across all the layers. In terms of external applications, I partially agree with you, right? If you have a radar or you have a camera or a LiDAR, do you really need the 6G as a sensor? I think that there's two answers that are pointing to yes. The one is that, okay, it can reduce cost if you don't do monostatic sensing, right? Because you don't need to change anything, actually. You just use the signals in a different way. And then the more compelling argument is it can increase redundancy. It's an additional sensor that you can use to check the other sensors. So it can provide integrity, and then you can use sensing for certain safety critical applications that you could not use it before.
Okay. Does anybody else want to comment on that? So are there any more questions? So I'll take one more, and then, we'll conclude the panel.
Thank you. Thank you for the panel, very interesting. I have a question about computing and also the integration of telecom companies and operators of services based on generative AI and LLMs. Do you think the infrastructure that the telecom operators have today is sufficient to support the new load coming from these services based on LLM, or they should invest in the future on new infrastructure, or just collaborate with third-party companies that are more specialized on this high scalability infrastructure? Thank you.
Very good question. Honestly, as a telecom, we are responsible because the new wave of traffic for the network will come due to AI. So I think if this Nokia Bell Labs is estimating around 1,000 exabyte per month of data coming out of AI in 2033. So around 24, I think, if I'm not mistaken, 24% of the traffic coming in 2030 will be basically because of AI. People, consumers, and their mobile or enterprises will generate content and traffic or demand for traffic because of the AI. So from one end, we are responsible to accommodate this traffic, maybe hosting a lot of this application that is requiring processing for GPUs in our country, in our data centers. And from other ends, we need also to have our own internal capability to have generative AI or AI that will orchestrate my network or to manage my network, because it will be too complex to be managed by humans. Do we have the capabilities? We have a lot of data centers internally, but and we are expanding our infrastructure with different partners. As I said, we are in last GITEX, we shook hand and partners with different infrastructure like Sambenova, NVIDIA, of course, their suppliers of like Dell. We already have a long relationship. Beside of that, our strong relationship with the hyperscalers. And this is a very important partnership we are looking forward to enhance with Microsoft, and with Oracle. We are striking a balance that between relying on others and having our internal also capability.
Yeah, I think that was a very important question in terms of, whether our infrastructure can actually take, that kind of load in terms of data. So I'd like to conclude the panel. I'll just give 1 minute to each panelist. If there's any takeaway message you want to share with our audience here in terms from early research that has been happening around 6G, any message, any advice, for the researchers here, for, people from industry here that you would give based on what you've seen happening in the last couple of years in this area. So Henk, maybe we can start from there, just 1 minute, very quickly, and then we can just...
Sure. So I think we should not be too worried about the Gs. I think a lot of the things that were presented here at this conference, I mean, for instance, the presentations about stacked intelligent meta surfaces, I mean, these are very forward-looking, right? And we as researchers should be forward-looking. We should not think what's happening by 2030, but beyond that, also about HAPS and other technologies. So we should keep doing what we're doing and try to influence decision makers, operators, telecom equipment vendors, and so forth.
Yeah, for sure. Yeah, we do our part, and then they take whatever they want to take up, right? Najla.
I just want to say I'm very excited about AI. I think this will really change our life, honestly. And I'm not doing marketing for what I'm doing. It's really remarkable what especially generative AI will do. And there is a huge worry around it, definitely. And I don't know if you have seen some of the movies out there, Megan and Are You Afraid or something like that. I don't remember how AI and robots will take over. But be excited about what will happen. Let's embrace the change. As an industry, I think it's very important to keep hand in hand with the research centers.
I love that.
I really am proud of this work and partnership with the TII and the Khalifa universities, UAE University, beside the R&Ds of our existing partners, but most importantly with the local research centers here in the country. We already have some good partnership with Aspire, a subsidiary of Abu Dhabi Advanced TRA, which is in a way TIA also is there, in testing our network for their autonomous race. I think it was autonomous Formula 1 race, something like that. Okay. Which we were eager actually to be part of it, and I just want to say, let's be optimistic.
Yeah.
Let's be optimistic.
Yeah, that's great. That's wonderful, Marco.
I mean, so I agree with what Anka basically said. So I'm not sure now how many young researchers are basically in the room, but I think that sometimes, I mean, we try to follow too close or we try basically to define what the next generation is before too much in advance. Yeah. So I think that the beauty is really to try to discover this new thing. So as I was saying, people are working a lot on this integrated sensing and communications on the waveforms. I think that there are exciting research works that are coming out, I mean, to really to understand what the fundamental is. But then at the end of the day, what you see that are mapped into the standards or even in several European funded projects is how to adapt what already exists to make sensing, I mean, be part of the communication. So this is not, I mean, this is important. It's not basically super exciting for us. So I mean, you are in love with AI. I'm in love with metamaterials, possibly mimicking AI. So I mean, we need to find a way to work together, I guess, for doing that. So now, I mean, what I'm particularly excited about is this computing in any form, and to see what role, I mean, it could play for telecommunications. But I would also basically try to do blue sky research. I mean, is nice, but I mean, at a given point, it's always important to try to interact with companies and try to figure out what is going to happen. So I can see what at the beginning happened with this reconfigurable material. I mean, with other technologies, you see that all the times that these things stay in papers, nobody really care about. So it's really when a company is kicking. I was discussing before with some people in companies that are willing to test, to make tests, to prototype. So I think that we need to find a good balance between doing very top and fundamental research, and then to have to make an effort also to engage with companies. Yes, exactly. Yeah, but this does not have to be necessarily related to a generation, because then I mean there are other considerations that will make that technology into the G. Yeah.
Totally, I agree. Nawaf, we'll end with your thoughts.
To me, I guess one of the main takeaways is that this has been a great summit.
Yes.
Indeed. We need more summits. We need more events like that. I hope we, especially here in the UAE, in Abu Dhabi, we continue the conversation on 6G. We continue investment. I'm sure many of my colleagues here would agree. More funding. That's one takeaway. Second takeaway is still we have a long way ahead. It is exciting. There are a lot of interesting ideas and directions, but ultimately, you know, there will be kind of a bottom line that will decide what will be part of the standard. There are, just mentioning one example because it's relating to the work we do. So do a lot of work in synchronization, not frame synchronization, but kind of PNT timing. And there's even especially for distributed MIMO, I mean, you need to synchronize, and the accuracies have been getting tighter and tighter. So I wonder maybe for some of what's being proposed for 6G, is it even feasible
in terms of the
available timing sources? So that's just a question always in the back of my head. Is that even feasible going forward? But yeah, but still exciting.
Yes.
Hope for more.
I agree. Lots of excitement in store for the next couple of years until we figure out, you know, and then we keep working, you know, we look forward, we keep working. So thank you so much to all the panelists. I think this has been a great discussion, and like you said, at the end of the summit, so I think it was pretty...
And thank you to our brilliant moderator as well.
Thank you very much. Thank you very much. Thank you, everybody, for attending.
Thank you.
Okay, good afternoon, everybody. Then we can start the last panel, but not the least. I will invite my speakers, the panelists, to join me, and then I will introduce you the panelists. Then, yes, please. Okay. Okay, then it's a great honor to moderate this panel because not only for the importance and the relevance of the topic, but also because for the speakers that are here. But we are in the tricky position of to be in the middle between the people and then the weekend. Let's see if we can run quickly on this panel. Then the panel is about the importance of cybersecurity in the 6G and how, for instance, in particular, the AI and a large language model can create some impact on this sector. But before to start, I will introduce briefly the distinguished panelists that are part of this talk. The first one is Professor Ernesto Damiani, who is the Dean of the College of Computing and Mathematics at Khalifa University. Then we have Dr. Mohammed Alani from the RTI of Dubai, and we have Dr. Michael Baidley, then from TII, and last but not least, my friend Dr. Hussam Al-Hadi from University of Dubai. Then I will start with brief questions for all of you, and in particular, the main question is how we can secure the environment, in particular network environment, against sophisticated cyber attacks. So this is let's say, the free route of our panel. But I start with Professor Damiani then with this question. Given that with the integration, we are enlarging the surface of technology. In particular, we are integrating AI everywhere today. This is the hot topic. And the integration of AI and large language model, network security, how you evaluate the possibility to use AI, in particular LLM, as a useful tool to create proactive threat detection and mitigation for 5G and 6G networks?
So,
yes,
this is a very difficult, or if you prefer, a question that would require a lot of time, and I'm not trying to answer it entirely. I would like to make a couple of comments. First of all, the notion of why the use of AI on one side and the use of LLM on the other. So certainly what we are going to see, what we see already in 5G, because this is the result of a number of projects that, if you look at the TMRF project, for example, the project that are done by the mobile operators and their suppliers together, TMRF projects, you see increasing interest in being autonomous from the point of view of security decisions. And this is already true for 5G. Basically, you have this capability of the network to do computations, and I'm not referring now to the physical layer computations that we have been hearing about all day. I'm talking about the computation along the cloud continuum, the computation along the network infrastructure. So the network can do computation a lot, I'm old enough to remember the slogan, the network is the computer, right? So we are now closer to a situation in which the network is also a computer, and for example, it can do threat identification. It can do computations that will then lead to a change in behavior, to deployment of controls. So certainly the notion that there is an increasing autonomy ahead of us in managing the security needs and deploying the security controls on the part of the network in order to achieve a certain level of security, I believe that this is something that is it's not just for 6G, it's already in 5G. We are seeing this, in the deployment of 5G, we are seeing this. On the other hand, what does this have to do with AI? Well, the notion that in order to do automatically a certain type of reaction, so to detect automatically or semi-automatically certain situations, and then to deploy autonomous reactions to those situations, for example, to change configurations of certain controls, the network has to do an inference. Look at the input data, and so now the network is also much more knowledgeable about itself. It knows a lot more than it used to be, because it's more digitalized, so we know a lot about the network operation. And so applying AI is a way to try to make an inference about the network state itself that will lead to an action, a reaction in terms of changing configuration, for example, for security. So I see this certainly as a very interesting perspective, using AI for that, using AI for supporting the autonomy of the network in order to make decisions that have to do with its security posture and profile. Certainly we are looking at that for 5G. The suppliers are basically promising this for 5G, and certainly maybe the 6G network already will have a very high degree of autonomy in terms of keeping a certain type of security posture to achieve certain security objectives. Now, what is the problem? Why AI is not a synonym of LLMs? So why are we looking at LLMs specifically as the type of AI that will support the network autonomy? There are other models that we could use, of course, right? So you can use predictors, you can use anomaly detectors, you can, in the variation of what we would call traditional AI, they can be, of course, AI models of different types. Why are we looking specifically at LLM? Well, there are some technical reasons why we are looking at LLM for this type of support. First of all, because the notion is that in LLM we have a model of generation, which is foundation model plus tuning, which is probably easier to deploy than traditional machine learning for this type of autonomy support. And I will finish just by clarifying a little bit. If you try to train a model that will suggest you what to do when you read a certain type of data about the network operation, and this tells you what to do in terms of changing a configuration, in order to train that model, you can either have the data and you don't. I've been in a number of European projects on this. You just don't. There's no reason to believe that you will have them in the future. You can generate the data. You can traditionally, with the GANs, with that type of thing. Problem is that, it's not that easy to have traditional generative models especially when you're talking network behavior. The distributions are not Gaussian, the GAN models sort of, let's say, sputter. What can we do? Well, we can have a foundational model about the behavior of complex systems, which is trained about the knowledge of the engineer, also the symbolic knowledge, why not, with a lot of metadata in, and then we can try to tune it to help to make the security decisions. This is something that is more realistic in terms of the deployment, in my opinion. So this is why everybody is talking about it. Have I seen any vertical tuning done successfully for security management of complex networks? No. I have heard many talks, I've seen many PowerPoint warriors, but I haven't seen any deployment. So I'm saying that it's promising, I'm saying that it's interesting. Of course, the notion is that LLM as the basic tool for network autonomy in security are still a promise at the moment. I don't see the use cases ready. Okay, I'll stop here.
Thank you very much, Professor. That maybe we can use this last sentence as a generic question for all of you. If it's a hype or not, the adaptation of LLM in this field. But let's speak to Dr. Mohammed, then asking in particular that, okay, AI is just one point, but we have also the usage of IoT, Internet of Things. Then I think that is better to talk today about Internet of Everything. And then this is another implication, because we are enlarging the surface of attacks in this case, not only the surface of the usage of Internet and the network, etc. But in your opinion, if you have to select some most relevant challenges in securing the IoT perimeter, what is your recommendation?
Well, thank you. I can talk about IoT security for years, not hours, actually. IoT security have been a challenge for a long time. It's one of the weakest links in cybersecurity. There have been several folds of these challenges. Some of them are technical. During our research, we found vendors that use firmware that have been, open sourced 15 years ago and has known vulnerabilities, and they deliberately choose to use it, no matter what, even though it has well-known vulnerabilities. We have seen IoT systems that cannot accept patches and updates, even though they have well-known vulnerabilities. We have seen IoT devices that have hard-coded passwords even. So we stopped blaming people for not changing the password, because sometimes it is physically not possible to change the password because it's baked into the firmware. And with all these challenges, I think AI presents itself as a possible tool to help in that fight against cyber attacks. I think that currently we're being forced to think far away from on-device solutions because of the limitations of these IoT devices. And once we move to network-based security solutions, I think old school AI presents itself as anomaly detection in traffic, detecting malware even in traffic could be something that would help in the challenges in AI. Of course, another challenge is user awareness as well. Choosing cost over security is a very big challenge that, when you find a home IoT device that's 20% the cost of something expensive but more secure, we see a lot of users opt for the cheaper solution even though it's not that secure. So that's also another direction that we need to move in, which is increasing awareness about the dangers of choosing cheap over secure, because I cannot only blame the vendors. We need to make sure that our users are also aware of the consequences in terms of security of what devices they choose to use.
Yeah, thanks. Also, this is another concept maybe that I can use for the second round of the question, how we can spread awareness among not only the people, but also the decision makers in particular, etc. But I will back to you in the second round. Thanks, Dr. Mohammed. Then let now ask Dr. Michael the specific question on how we can create a robust security architecture for 6G. In your opinion, then we are talking about the surface of attacks, but also we need to have a robustness. Okay, then in the 6G network, can you share with us some insight?
Yeah, sure. I mean, I think there's not really much I could say just now that hasn't been said over the past 2 days about AI. I mean, you know, we've had this discussion again and again that AI really is the solution for a lot of the problems and challenges we're seeing in 6G with the advent of generative AI. But really, I think there's two aspects to this. So one is the cyber security, and I think this is where there's a very clear path of how generative AI can and how generative AI will help secure 6G networks. I mean, at the moment, of course, maybe the capabilities are not really there. We've got Telecom GPT out there, for example. And I think the initial phase will see people using this in order to kind of identify problems to operators, and then operators can then go and actually solve these problems. The next phase after that, and the bigger research challenge, is how can you have a closed-loop AI, and some of the panelists today did touch on that. And then once you get to that point, you then need to understand what's happening within these networks to make sure, and I think I asked this question earlier, to make sure that the AI isn't kind of feeding back on itself and causing your network issues. So that's the that's the cyber security aspects. The other half of that is the physical security aspects. So when we talk about security, we don't just mean, is there a malicious force within my network? When we talk about security, like you would food security, housing security, how do you have communication security? Now, we've seen, especially this year, the impact of climate change, the impact of disasters, and how this can really affect communication networks. So there's an aspect of how can we use AI in order to provide physical security for the networks? How can we build resilience and failover? Can we use AI in order to help us predict where our communication networks will fail, and then build backups within the system? So I think those are really the two main areas. The first one, cyber, is straightforward. Then I think the physical security aspects is something that's not really been discussed yet, but will be important going forward.
Thanks so much, and also maybe that's interesting to talk about how to implement cyber and physical resilience or security, and then. But this is another story. Thanks, Michael, for that. I give the mic now to Dr. Rustem, asking, in particular, we're talking about vulnerabilities and the problem of the security, etc. But in your opinion, which kind of vulnerabilities are related to the 6G, and how we have to adapt the cybersecurity to manage these kind of vulnerabilities?
Oh, first of all, thank you, Dr. Luigi, I'm very delighted actually to be here with the esteemed panelists, and thanks for TII and for the organizer for the invitation. Well, it's actually very hard to say. I mean, when the internet came, we think that the internet actually going to change our life, but when the IoT came, definitely changed everything. If the IoT is actually, we consider it as our sensors in the environment, the 6G and the 5G will be the backbone for this technology. And definitely we need to understand the relation between them. It's very hard actually to highlight what's the vulnerability in such systems. I mean, I attended a keynote talk yesterday, one of the conferences in Dubai, and the keynote speaker, he was talking about surprising stories, 7 surprising stories that change our view about cybersecurity. He was mentioning actually attacks about stuckness, attacks about attacking the power plant, the supply chains, and how they are very sophisticated. Unfortunately, we shifted from our digital world to the cyber-physical world. So basically, we are not limited to only what is actually the patching or anything, but we are also vulnerable for material as an attack. And for instance, some researchers from Rice University, they invented an attack called meta service in the middle. So basically, this is like a material that can be in the middle between the sender and the receiver. And this is not digital. So basically, so we cannot define what is the critical vulnerability. We have to be aware. We have to be proactive all the time. It's our duty, at least, to investigate what is actually the risk, and we try to provide some kind of countermeasures or some kind of resilience solutions. The beginning of this month, I believe there is a newsletter. They announced about an attack happened from hacker groups. They call it Salt Typhoon. Maybe from the name you can tell from where they are. But this Salt Typhoon, what they did is actually attacking several telecommunication companies in certain country, and they managed actually to gather a lot of call details, records, and they managed to collect information about the location of some of the users. And this is actually going to be a little bit risky for any type of system when actually you are trying to protect the human identity or the human privacy, the people's privacy. Some of them may be actually relevant to military, so you need to protect their location. So what we do, for instance, we can try actually to highlight a few projects. We can try actually to propose thesis, okay, for the students to try to hide the identity of the people, okay, in the 6G or 5G network. So try to find a way where we can provide privacy, we can provide an authentication with the key agreement, protocols like this. So, as I said, where it's actually critical, we have to be alert. As a cybersecurity people, we always need to be thinking about ahead. We are not optimistic about any technology. Everything is actually going to come forward as a new things. So this is just my input in this matter.
Thanks very much, Osama, also because I really appreciate your concept of proactivity, and then we cannot stop the progress, in particular the technology landscape, but we can manage and then to implement some proactive measure to manage this evolution. No.
If I might just also comment on that as well, it's funny that you're talking about privacy, and it's not even sort of malicious attacks on our privacy that we really need to be worried about, but also actually intended use. So I don't know if you have read about this, but of course there's this running app, I think it's called Strava, Swedish one, and people were actually using the public updates not of, for example, the President of the United States, but as bodyguards, to actually find out where the President was based on the updates of the bodyguards. And I think given the expanse of of IoT devices and the number of different vendors and competing platforms, et cetera, it's very difficult to sometimes protect against this kind of unintended consequences of the technologies.
Also, you want to reply or want to add something?
No, I agree with him 100%. I mean, it's not only about defining the target person, but actually understanding the environment of this person and try to allocate how we can actually deceive. I mean, the things actually, as he brought it up, attackers are getting smarter. And right now, maybe with utilizing some AI technology, they can get more directed way to actually know where to attack, where is the vulnerability. So I agree 100%. This is actually one of the scenarios.
Excellent. Let's give the mic again to Professor Damiani and all of you. This is a question for all of you. If you have to select a priority and then to talk about this priority in front of the audience, but also in particular in front of the decision makers, which kind of a priority you will list?
Well, again, a difficult question. I would like to just make this comment. Here we're talking, not generically speaking, of the security of IoT applications in general. I think that we are talking about the redesign of the next generation of the network and how this new redesign, sixth generation of network, can handle the security challenges that IoT is creating. Of course, you can handle them today. You try to handle them today. But it's a weak link. But of course, we are not. We are fighting even today to try to secure the IoT applications in general. But the 6G notion, which I don't know which should be the priority or not. Certainly, it's something that is being discussed in the community, is whether the network can be designed from the beginning in order to be able, by its own intelligence and capability, to basically minimize or alleviate the threats that the IoT scenario is, but not just the IoT, that the use cases of 6G in the previous panel, there was a little bit of a problem to name a few use cases for 6G, but let's say that we have those use cases, and then we want to design the network. So the priority is, can we have an intelligent network that can make things easier in handling the security issues that certainly the new use cases will pose? And the answer to this, this certainly is a potential priority. It will cost a lot of money. It will cost a lot of effort in the 6G design to have, as a first-class citizen, the security alleviation with respect to the potential attacks. I would like just to make a quick comment. Why is it costly? Because in order to be able to minimize the security concerns, the 6G already in the network, the 6G network will have to be able to handle a lot of situations, we'll be able to modify. And the tendency of migrating security functionality towards the physical layer that we have been hearing in this summit, but we are here. Well, it means that the technology, the network technology of the 6G will be different from the 5G enough to be able to do that. I would like to make only one example. Physical layer security and the so-called death of crypto. So what does it mean, a death of crypto? Why are we spending money to encrypt, while we could have a system in which the only destination that will be actually reached by the message is the one that has title to hear that? So in that case, if I could arrange a system like that, I don't need any sort of crypto. It's plain text because it's the only recipient. I'm, of course, extremizing now. So if we could have a capability of the network to modify its own physical layer in such a way to provide confidentiality, security, integrity, authenticity, provenance, all the properties that we struggle to do at the upper layers right now, well, we have a network that will basically incorporate security as a first-class citizen. The only problem is that some of those that I mentioned are, of course, dreams that are not substantiated by realities. Other are dreams that could become true at the expense of an enormous cost of substitution of the technology, because if you really want to do waveform engineering as a way to provide confidentiality, well, the military pay for that, because of course they do waveform engineering because lives depend on the secrecy of the communication. Do we really want to do that for the ordinary traffic on the internet? Isn't encryption good enough? So the priority could be having a network that has security as a first-class citizens in its own operation, thanks to its own intelligence. On the other hand, we should keep in mind, especially the people who buy, the operators, that it will cost much more. Because if you want, go to the suppliers and ask them physical layer security instead of crypto, when appropriate, the equipment, the waveform equipment, the beamforming equipment, all that type of equipment will cost you much more than it does now when the crypto is done on the bits and not in the signals. So I stop here, but.
Thank you very much. And then the second question is who will pay for this cost? And then, but we don't have time. Mohammed, please.
Yes, I think. I won't be able to talk about physical security and the cost of providing security at the physical layer, but I think that 6G can promise to have a layer of security maybe on some SDN level, software-defined network, where we can actually, due to the amount of low latency and the amount of bandwidth available, it might be feasible to add a layer of security in there somewhere between the third and fourth layer, so that we would have actual intrusion detection systems built into the network, so that you don't need to have on-device intrusion detection system. You don't need anti-malware software, because it's all software-based at the end. It's all the networks, we've been using IP-based networks for the past 2 generations of phones. So we might as well try to embed some layer of security. That might be a good priority for 6G research.
Thanks. Thank you so much. Mike?
Yeah, I was just going to say it's kind of interesting that you bring up the SDN angle, because I think with these new generative AI models, with these LLMs, or if you're doing kind of large behavioral models or large action models in the future for networks, then SDN concepts are really quite important. Having this centralized entity and then having this northbound interface that allows you to then send these actions back out into the network. And I think this is really where kind of ultra low latency technologies for 6G can really help this concept and really support the generative AI concept in 6G.
Thank you very much. Listen, please.
Yeah, I agree with all the panelists. I mean, it's one of the challenges that you have to give a right standardization for such things, especially when you deal with IoT. We have a problem that some of them could actually come from a certain area, and the people, as Dr. Muhammad mentioned, that could feel, yeah, they can compromise security over cost. But if we can adopt something like security by designs, as Professor Ernesto mentioning, if we can actually implement it in the hardware layer, just shift a little bit the face of what we are actually expecting security to be. We don't want to be as a cryptographic protocol, not anymore, okay? We are trying actually to make something similar to the zero trust. So we are trying actually, for instance, like from an academic background, when we actually try to develop courses, we are getting interest what courses can be shifted now. I mean, network security, cryptography are all the news. It's important. I'm not saying it's not important. It's important. But within the IoT and within the 6G, within these technology of cyber-physical system, we have to consider courses like cyber-physical system security or something like a zero trust, for instance. So the students will actually understand how to build a castle inside a castle. So you are actually trying to protect your system to the core, and it already exists. I mean, I can see this actually in the cloud. We can see this on several proposed technologies, like some of them. I don't know about the Dubai taxi. It's new things. I'm sure you are heard about it. So basically, I'm sure that they have several replicate system in order to secure the environment and maybe also to provide zero trust. So I don't want to take a lot of time, but my point is actually this is very important, and we need to define the vulnerability that we have at the moment and how we can actually move forward to implement something better for us all.
Excellent. Thank you very much. And I don't want to abuse of the time because we are in the weekend. And then let me to thank the panelists and also the organizers. Thanks Lina and also the TII and to organize this very interesting and timely summit, and then also to organize the panel inside the summit on these topics. Thanks again, and then have a nice weekend. Thank you.
Thank you.
Thank you so much. So we are reaching the end of the event of the 6G Summit. I would like to thank so much all the participants, all the people that did not hesitate to come, and they say yes very fastly over all the world. We are pretty proud of this tight relationship of collaboration with all the people that were invited, and we are excited to gain more and more public people and more collaboration. As you know, this is the 3rd edition of 6G Summit. We are pushing to make it also for next year, and we will continue making communication on that. And we thank you so much. And I think that the success of this event is also because of the participants and the quality of the talks and the quality of the interaction that we can get here in this such event. So thank you for all our collaborators, for all the people that give us a talk, and see you next year, and wish you all the best for more exciting ideas, challenges on 5G, which there is a lot of things to do, as we heard, and also AI, security, all these challenges that you will face in the future. Let's dream for next G. Thank you so much. See you next year.